Hello and welcome back to the channel. Today I've got my biggest video to date. This is an introduction to fundamental game development from scratch, only using SDL3 and its related libraries. We won't be using an existing game engine, and we'll build everything ourselves so we understand how the guts of a game engine work. I'll use C, C++, and CMake to build a platformer game that'll serve as a robust foundation for us to expand, optimize, and build on top of for future videos. This video is about tackling fundamental game development, and I won't focus on optimization and architecture as much. I want this to be fun and engaging and help beginners get to a point where they're moving, animating, and making noise with their games rather than getting bogged down in programming principles and optimization techniques. We'll have plenty of time for those techniques in upcoming videos. I hope you follow this video start to end, as it's an iterative process, and by the end of it all, you'll have the know-how and engine to continue expanding and building your own type of game as you see fit. And now with all the introductions out of the way, let's open up the project and get started. I've created this project using the Visual Studio CMake template, but you can follow along on any platform and using any compiler. Everything is cross-platform and transferable. Later on, I even show you how to do things from the terminal in case you're not using Visual Studio to set up your CMake project. Taking a quick look at the CMake list files, the root one in the project simply brings in a secondary one, which is where the actual executable is set up. This is where we're going to issue the find package commands and set up the SDL library for linking. We start off by telling CMake that we want to find the SDL3 library. We do that by issuing find package SDL3 and marking it required to make sure that CMake fails if it can't find it. Looking at the output, we see that CMake can't find SDL3, so we have to download it and help it figure out where to find it. Let's head over to the SDL website and click on the SDL releases link. And after being taken to the GitHub releases page, we can download whatever devel package we need for our platform. I'm using Visual Studio with Visual C, so I'm going to get the SDL3 devel vc.zip version, but if you're using MingGW, you can get that one instead. If you're on macOS, the easiest thing might be to just install it using Homebrew, and if you're on Linux, you could use whatever package manager is on your system. Another option is to download the source code, compile it, and then install the library on your system, which is actually quite easy to do. I have a video on how to do that using CMake, and there's going to be a link in the description. After extracting the library to my SDKs folder, let's take a look at the contents. There's the include folder, which has all the header files for SDL3. We've got the lib folder, which is where we have all the runtime and development libraries. And the CMake folder, which is where the actual package config files are that are going to tell CMake where to find everything and help us link against the library. Now we need to go back to Visual Studio and set up our build so that CMake can actually find the library on our disk. The first thing we're going to take a look at is the CMake presets.json file. This is what configures the various builds that are available to our project. We don't want to change this file because this one is shared amongst all developers on a project. What we want to do is make a copy of that file and name it CMake user presets, which is where a developer would want to put paths that are specific to their computer. Inside that file, we can delete everything except for the x64 debug build. After that, we need to change the name of the build to x64 debug user and change the display name to x64 debug user as well so that we can differentiate it from the other one. We're also going to change where this build inherits from, and that'll be the original x64 debug build that's defined in the CMake presets.json file. We're simply inheriting all the properties from there. We can also delete the architecture field and any cache variables that are still defined. Those are all inherited from the original x64 debug build in the CMake presets.json file. Next, we're going to take the path of the SDL3 library we just downloaded and pass it to CMake using the CMake prefix path variable. We can provide this variable using the cache variables object. You can separate a number of different paths with semicolon on Windows or colon on macOS and Linux. If you save, CMake will try to regenerate the build, but it'll fail to find SDL once again. This is because we have to change the active build at the top in the toolbar. After doing that, CMake will reconfigure the project, find the SDL3 library, and successfully generate the build files for us. If you're working on macOS, Linux, or just the Visual Studio command line tools, create the build directory, then run CMake-s, the path to the root CMake list.txt file, then -d and the CMake prefix path variable, and then the path to the SDL3 library we just extracted. Then -b and the path to the build directory you just created. When you hit enter, CMake will run, find the library, and generate the build files inside the build directory. Then you can just compile the project by running CMake --build space and the name of the build directory you just created. Everything should compile successfully, and we can move on to writing some SDL code. If we try to include the SDL.h header, we won't be able to find it because we have yet to tell CMake to actually link our executable against the SDL3 library. We need to head back over to our CMake list.txt file and use the target link libraries function, then passing in the name of our executable target and linking against the SDL3 library inside of the SDL3 namespace. Once we save this file, CMake reruns the configuration, adds SDL3 to the compiler header search paths, and makes sure that the linker links our executable against the SDL library. Running compile, we see that the header is included successfully and the project builds. Now we can initialize SDL by calling the SDL init function and passing in SDL init video as the flag. This initializes the SDL video subsystem. Also be sure to call SDL quit at the end of the program to make sure that the program cleans up after itself. Changing the startup target at the top in the toolbar, we can run the application by clicking that run button. Once we do that, we see a different error. The program's not able to link against the SDL3 Runtime DLL. Here's how we fix that. Again, make sure that the startup target is set, and then go to Debug and then choose Debug and Launch Settings. Here we're going to add the env section and set the path variable for our running executable. Then we can go back to the folder where we extracted the SDL3 library, go into the lib folder, x64, and then copy that path. We paste that in and set it as the path for our executable. Then add semicolon, %path% to make sure the executable receives the full system path as well. This is a better approach than copying the DLL to the output directory where the executable is, because that path gets deleted when the project is rebuilt. In order for SDL to properly initialize fully, it needs to be able to rename our main function and replace it with its own main function where it does some setup and eventually calls our main in order to start the program. In the previous version of SDL, we would be linking our executable against another library called SDL main, but with SDL3, we simply include the SDL main.h file. If we compile now though, we're going to see a linker error telling us that SDL main is not defined. This is because SDL tries to rename our main function to SDL main and then in turn calls our main, which it had previously renamed to SDL main. In order for SDL to be able to find our main function, it has to have a signature including argc, which is the argument count, and argv, which are the argument values coming in from the command line. Now we can add some error checking to make sure that SDL is able to successfully initialize. If there's an error, we use the SDL show simple message box function and display an error message for the user. We also return in order to exit the program with a return value of 1, signaling an error. We can now move on to creating our window. We do that by creating a pointer to an SDL window object and then calling SDL create window. First we pass in the window title and then we create some variables to hold the window dimensions. This is so when we start supporting resizing later on, we can keep track of those sizes as they change. The final parameter is the window flags, which we're going to pass 0 and ignore for now. I also want to create a cleanup function, which we can use to group all of our resource deallocation in one place. It's going to receive an SDL window pointer and then call SDL destroy window in the body, followed by SDL quit. Then I forward declare it at the top, just so I can keep the utility functions at the bottom and main at the top. We also want to replace our existing SDL quit call at the bottom of the program with the cleanup function call passing in the window. Then, of course, we want to check if the window was actually created, and if it's not, we use our show simple message box function again to display an error for the user. We call cleanup and then return 1 to exit the program. If we run the program now, what we're going to see is that the window is just going to open and close very quickly. This is because SDL is opening the window and then the program is just running through to the cleanup function and exiting right away. What we need to do is start creating our main game loop, and then inside of that, we need to run a secondary loop, which is going to be responsible for handling platform, window, and user input events down the line. Our top level while loop is kept running by a boolean called running, which we set to true. Inside of our main loop, our secondary loop calls SDL poll event consistently, which returns true in the case of an event. If there is an event, it fills an SDL event structure that we've passed in by pointer with the relevant details pertaining to the event. The only event we currently care about is SDL Event Quit, which is what happens when the user clicks the close button on the window. In such a case, we set running to false, which will break us out of the top level game loop, allowing the application to run through to the bottom, clean up, and exit. If we now compile and run the application, the window shows up and stays, allowing us to move it around, and we can also click close to exit. I'd also like to create an SDLState structure, which is going to hold all the important SDL objects in state. This way, when we handle SDL initialization and cleanup, we don't have to pass around the individual pointers and objects to SDLState. We can just pass around a single SDLState object. Currently, we have the SDL window in the state, as well as an SDL renderer, which we're going to deal with shortly. Further in the code, make sure you replace every instance of win, our SDL window, with the state.win. Then head down to the cleanup function and change the signature so that it takes a reference to an SDLState object. Then go to all the call sites where cleanup is being called and pass in the state object instead. Don't forget to also update the forward declaration of the cleanup function at the top of the file. A quick compile and run to make sure that we didn't break anything in the process, and we're ready to get to business. We're going to start off by creating the SDL renderer object. We do that by creating a pointer to an SDL renderer and calling SDL create renderer, passing our window, and null pointer for the name of the device we wish to use for rendering. Passing null here tells SDL to pick one for us, but eventually we could write some code to auto-select the most appropriate device or let users select it. For now, let's leave it like this. We should immediately also update the cleanup function and make sure we destroy the renderer before destroying our window. This is done by calling SDL destroy renderer and passing our state.renderer pointer. Then we want to make sure that we don't get back null from SDL create renderer and we actually successfully create one. And if we don't, we simply show an error message, clean up, and exit the program. Let's scroll down to our main game loop now. Underneath the inner loop, let's start adding some drawing commands. Normally, you first check for events, handle them, and then you draw. We're going to do something simple at first, just clearing the screen. We do that by calling SDL set render draw color, passing in the renderer, and 255 across all color components for pure white. Then we simply call render clear and pass the renderer, which will actually clear the pixels to white. Then we need to make sure we call SDL render present, again passing in our renderer, which will flip the back buffer to the front and present what we've done. The previous front buffer becomes the back buffer, and we're ready to draw again in the next loop iteration. When we run the application, we see the background color has changed to white and everything is working as expected. For the next part of the lesson, I want us to start doing stuff that's a little bit more interesting. I've drawn this little pixel art guy and given him an idle animation so that we have something to work with. I'm by no means a good pixel artist, but this should be enough to keep us going and to demonstrate the concepts clearly. Then I exported the various frames of animation into a single sprite sheet, which is what you're seeing on the screen right now. What we need is a way to load this image easily into SDL and to draw it on the screen. We also need to be able to draw individual pieces of this image so that we can render out our animation like a flipbook. Further into the tutorials, I plan on getting into more texture packing techniques and optimizing things so that we can keep most of our graphics in individual sprite sheets rather than one for every type of animation. But that's not really necessary, and we'll get into optimizations once we do more of the fun stuff. There are a number of different libraries that we could use to load images into SDL, but we're going to use SDL Image. It's very full-featured, it works very well with SDL, and it lets us get to work without fiddling with any of the intricacies of image loading. When you click on the GitHub link, it's going to take you to the SDL image releases on the official GitHub. Make sure you show all releases and download a develop package that's appropriate for your compiler. I'm using Visual Studio, so I'm going to get the vc.zip version. There's also the option of downloading the source code, compiling it, and installing it on your system, which you can pause here and look at the videos on my channel on how to do that, or you could install it using your system's package manager, whatever works best for you. Extracting a development package, it's clear that the structure is the same as what we installed previously with the SDL library. There's the includes, the libs, and the CMake files required for importing the package into our project build. So we're going to go through the motions just like we did originally and tell our CMake where to find it and to link against the project. We start by adding another call to find package in our CMake list.txt. This time we're looking for SDL3 underscore image, once again marking the dependency as required. And of course CMake can't find the library because we haven't actually told it where it is. Now because my CMake user presets.txt file is not in source control, it's not showing up in the project file list. So you have to go File, Open, and navigate to the file manually. Then once again, we copy the path to the root of the library. But we'll notice that in Visual Studio, there's a bug that when you paste the second path in the list, it adds a bunch of unnecessary slashes. Quickly fixing that and saving, going back to our CMake list file, we see the squigglies are gone under Find Package and that CMake ran successfully and found the library for us. We also need to go to our target link libraries and add SDL3 underscore image from the SDL3 underscore image namespace to our SDL3 demo target. Now CMake will link against that library and will also add the headers to the search path. We can include them in our source file and build successfully. Now let's scroll down above our game loop and create another section where we're going to be doing some asset loading. This is where we're going to load our image into an SDL texture. An SDL texture is a piece of memory holding an image on the graphics card. The imgLoadTexture function from SDL image loads the image at the provided path into a texture object on the GPU, which makes it easy for the graphics card to draw these graphics on our screen, but also means that we can't directly read those bits of memory using our CPU, which is fine because all we want to do is load this image and draw it to the screen. If we did want to load this texture into a memory that we can actually get to and manipulate, then we would have to load it into an SDL surface object. We're not going to be using that for now, but just keep that difference in mind. SDL textures are on the GPU, and an SDL surface is loaded into system memory. We also want to make sure that we call SDL destroy texture, which will free the VRAM memory that was allocated for the texture. We do this at the end of the program above our cleanup call. I want to keep game assets loaded and cleaned up separately from the rest of the program. It's good to get into this way of thinking right now, because when this program actually becomes a game, you will probably want to load and unload level data independently from the start and end of the actual program. Now we can move on to actually drawing this texture onto the screen. Scrolling down to our game loop, and underneath the render clear call, after the screen has been cleared, make a call to SDL render texture, passing in our renderer, our texture object, and null pointer for the other two parameters. Now if we compile and run, the program will compile, but we're going to see a runtime error telling us that the SDL image Runtime DLL is not found on our path. Let's fix that real quick. Going back to our debug and launch settings, we need to include the SDL3 image Runtime DLL to the existing path that we have from setting up the SDL3 library. Go into the lib folder, x64, and copy that path. Then paste it after the SDL3 library path that we had added earlier, and make sure you add the necessary semicolons. If you see this extra slashes bug like me, just clean them up and make sure that there's only 2 slashes instead of 4. If you're not using Visual Studio and you're on macOS, Linux, or MingGW on Windows, just be sure to install SDL3 image properly on your system, and the program will be able to find the runtime library. If we run the program now, we don't see the error, but we still see that same white screen we had before. Let's fire up the debugger and see if there's a problem. I'm going to scroll up to our loading code and put a breakpoint just to see what we get back from imgLoadTexture. Hovering over the idle text variable, we see that it returned null. This is because SDL3 image can't find our image file. the program executable is running inside the build output directory the Visual Studio produces when it compiles the program. Our data directory and idle.png are in the root of the project. We're going to tell Visual Studio how to run our project and set the current working directory to the root of the project. This will make sure that the data directory is accessible at runtime. Going back to our launch settings, we're going to add the currentDir property after our env property. Then we're going to open the path to the root of the project, copy the absolute path on our disk, and set the currentDir property to the root of the project. If we run the program now, we see that the image has been successfully loaded, but it's being drawn and stretched across the entire window, which is obviously not what we're looking for. I quickly want to change our background color to something a little darker and easier on the eyes. The window is being filled by a texture because what we have is a sprite sheet, and we just want to take a portion of that image and draw it onto the screen. What we need is to define an instance of SDL Rect and define the source portion of that image that we want to draw. So we specify the X coordinate, Y coordinate, and the width and height of the portion of that image that we want to draw, and give that to SDL render texture. When we do this, we see that only that portion that we requested has been drawn, but it's still being stretched across the entire window. You'll also notice that it looks really blurry and it really doesn't suit the pixelated aesthetic. We need to tell SDL that we want to use nearest neighbor scaling instead of the linear scaling, which is default. This will scale the pixels up without doing any kind of blending between them, which will retain the pixelated look that we're looking for. We do this with a call to SDL set texture scale mode, providing our texture and then setting the scaling mode. Make sure you do this after you load the texture, of course, so that SDL knows which texture to affect. If you want the scaling mode consistent across the entire game, you would have to call this on any texture that you use in the game. There is a way to actually set this once and not have to specify it for every texture, but we're going to do that later on and not worry about it for now. Let's just keep moving. We obviously don't want our sprite covering the entire window, so let's remedy that. We have yet to tell SDL where we actually want to draw that sprite. This is where the destination portion comes in. Once again, we define an SDL Rect, but this time we're telling SDL where we want to draw the piece that we selected using the source rect. We're telling SDL where we want to draw our sprite and what size it needs to be. In our case, it matches. It's 32 by 32 in each case, but if you specify a different size in the destination, it'll scale it accordingly. Clearly the sprite is pretty small on the screen, but instead of upping its size in the destination rect to something like 96 by 96, which seems to do the trick, we're going to leave it at 32 by 32 and instead do what's called setting a logical resolution for our game. This allows us to work with the same resolution regardless of the size of the window or full screen resolution of our game. This means that we can work with the same coordinates all the time and let SDL worry about how to scale things for us. If we scroll up above the section where we loaded the game asset, let's add another section where we can control the presentation of our game. Then a call to SDL set render logical presentation, taking in our renderer, a logical width, and a logical height resolution. And also setting the presentation style. I'm going to go with the letterbox, which means that SDL is going to retain the resolution I provided, the 640 by 320, regardless of the size of my window, and introduce black bars as needed in order to fill in the rest of the space. It will retain the aspect ratio of the game and allow us to work in a resolution that is independent of the window size or monitor resolution. There are other ways that SDL can scale things for us, such as integer scaling, but before we can demonstrate any of that, we should enable resizing so that we can actually change the window size. We can turn on resizing by going back to our create window call, and in the last parameter, which are the window flags, setting the SDL window resizable flag. Now if you compile and run, the application window shows up and we can resize it as needed. If we set the stretch presentation mode, we can clearly see what SDL is actually doing for us. In this case, it'll stretch the content of the window in various ways without retaining the aspect ratio. We don't want that because it'll create skewed and distorted sprites on our screen. We're going to leave it at letterbox and move forward. In order to properly handle window resizing, we need to also be able to get from SDL the new window dimensions after it has been resized. Heading back to our switch statement inside of our game loop, add another event case for SDL Event Window Resized. Upon receiving this event, we can use the event.window data1 and data2 to grab the new window dimensions. Putting a breakpoint here and looking with the debugger, you'll see that once I resize the window, we have the new window dimensions stored in those two fields. Then I'm just storing it in our width and height variables and keeping them in case we need them later on. And to quickly recap what Letterbox is doing for us, if I start resizing the window, SDL is maintaining the aspect ratio of our logical resolution regardless of the weird window dimensions that I throw at it. The body of our main function is starting to get a little crazy, so we're going to create a function called Initialize and move all the SDL initialization code out of main and into that function. I'm going to take everything from SDL init all the way down to set render logical presentation, and I'm going to put it inside the initialize function. Now I'm going to change things so this function returns a boolean, true or false, depending on whether initialization was successful. I'm also going to move the logical and window dimension variables into the SDLState structure. I'm also increasing the window size in order to make things a little nicer on the eyes. Now make sure that all references to those variables now use the state object. And then just call the initialize function from the top of main, and if it returns false, we exit the program. With that out of the way, let's see if we can make our character move. Head underneath the section where we have our game asset loading, and add another section where we can keep some variables for the gameplay elements. We're going to call the SDL getKeyboardState function, passing in a null pointer because we don't currently care about the number of keys that it's tracking. This function returns an array of booleans, and we can index into that array using SDL scan codes, which are defined in the SDL headers. These scan codes refer to physical keys on the keyboard, so we can use them directly to check if a key is currently being held or not. Also note that the array returned here is actually valid for the lifetime of the program. You don't actually have to call it every time you need the keyboard state, you just need to call it once at the beginning of your program and keep it around until the end of the program. Now we're going to add a variable that's going to keep track of the player's current x-axis position. This is the horizontal position of our player. Then we're going to set the x position in the destination rect further in our drawing code to dictate where we want the player along the x-axis. As an example, if I set the x position at 150, you'll see that the player is now drawn further to the right on the screen. Let's also move the player to the bottom of the screen because the way he's just floating at the top there doesn't look very good. For now, we're just going to create a variable called floor, and we're going to set it to the logical height of the screen. This is one of the benefits of working with a logical resolution rather than the actual resolution of our window or screen, is that we can guarantee that that is always going to be the bottom of the drawing area, regardless of the window size or resolution. Each of our sprites is 32 by 32. So if we want to draw the player at the bottom of the screen, we're going to take the bottom of the screen and subtract 32 to move it up 32 pixels, which will make it look like our player is standing at the bottom of the screen. We're doing this temporarily just while we're working with moving our player in the horizontal axis for now. When we introduce jumping into the game, obviously this won't suffice and we'll need to have a dynamic solution. Let's handle the player input now. Underneath the event loop, let's declare a variable called moveAmount. This will track how much we want to move the player for this frame. We check if the player is holding the A key, and if they are, we set the move amount to -75. This will make the player move 75 pixels to the left. Else, if the player is holding the D key, we set the move amount to +75, moving the player 75 pixels to the right. If we leave things like this, we're only checking if the player is holding A or D. We also want to handle the case where the player is holding both keys at once, In this case, the two directions cancel out and there's zero movement. So what I'm going to do is I'm going to change the else if to an if, and then I'm going to add -75 to move amount if they're holding A, and then add +75 if they're holding D. If they're holding both, then we're going to get a 0 because -75 plus +75 is 0. All that's left to do now is to add the move amount to our player X position every frame, and that should make our player move. What we see though is that the player is moving very fast. Maybe we should change that 75 to a 5. Well, it's still too fast. What about if we change it to something very small? That's better, but it's still really fast. We're approaching this completely the wrong way. We don't want to just use some arbitrary value for the player movement. This leads us into one of the most important topics in game development, and this is about managing time in our game. What you want to do is actually move the player a certain amount per second rather than just some arbitrary amount per frame. We want to move things according to time, not just frames. If we use frame-based movement, then the speed of our game will be dictated based on the speed of the person's machine, and everybody's got a different machine. This style of programming was acceptable back in the day when developers were strictly building video games for home consoles, which all had fixed specs. Different people's Nintendos all had the same clock speed, so the games would just run the same across all systems. This was also common to see in games from the 80s and 90s on home computers, and that's because a lot of those systems from that era were almost sold like game consoles and had very fixed hardware. Nowadays, people build their own systems and they buy computers from all kinds of places, and the specs are all over the place. Developers need to code things according to time rather than clock speeds. This is why we need to create a game loop that tracks time, and we're going to be moving our player according to the passage of time rather than the speed of our computer. If we head to the top of our game loop, let's create a 64-bit unsigned integer called nowTime. We're going to initialize this integer by calling SDL getTicks. What this function gives us is the amount of time that has elapsed in milliseconds since we initialized SDL. There's nothing special about this duration of time. This could very well represent the amount of time since January 1st, 1970, or it could be the time that's passed since you turn on your computer. It doesn't matter. What's important is that if we take the time that the previous frame started at and subtract it from the time that the current frame is starting at, that'll give us the length of time between those two frames in milliseconds. If we then convert that time to seconds, what we end up with is a fraction of a second. This fraction represents the amount of time it takes for one frame of our game to execute. Once we know that, we can describe our movements per second, meaning that 75 we used earlier represents how fast we want our player to move per second. And once we multiply that by our delta time, we can establish how far the player needs to move for a single frame of our game. In order to facilitate this, we need to subtract from our current now time the previous now time from the previous frame. And to do that, we create a variable called previous time, another unsigned 64-bit integer, declare it outside of our loop, and initialize it with a call to SDL getTicks. Then I go to the bottom of the loop and I set previous time to equal to the value of now time. You don't really have to put this at the bottom of the loop, but my brain just likes to see it there. Now when we get to the beginning of our next frame, our previous time variable will hold the old now time, which represents the start of the previous frame. Subtracting those two gives us our delta time. And since that's still in milliseconds, we have to divide by 1000 to get it as a fraction of a single second. What we now have is a very real game loop, a simple one, but it's one that we can use to drive our game using the passage of real time. When we start getting into more advanced things, perhaps doing physics or moving sprites quickly across the screen, we'll find that this approach is insufficient. We'll have to design a better game loop, but this basic approach goes a very long way and will be more than enough for what we're doing at the moment. All that's left now is to go to our movement code and to multiply our move amount by delta time before adding it to our player X position. Now our player's X position will change based on the amount of time our player should move for a single frame. And we're clearly ready for a job at Blizzard. To make this look nicer, we need to be able to flip the sprite depending on the direction that we're moving. In order to do that, let's call SDL render texture rotated instead of our previous render texture call. This takes a lot of the same parameters we're used to with render texture, but it can also receive an angle of rotation, a center point, but what we're interested in is the last parameter, allowing us to flip our sprite horizontally, vertically, or whatever. If we pass the SDL flip horizontal flag, we're going to see our sprite drawn flipped horizontally as demonstrated. And in order to make this follow our movement direction, we add a boolean outside of our loop called flip horizontal and initialize it to false. Then if the user presses the A key, we set flip horizontal to true, and if they press the D key, we set it to false. Back to our render texture rotated, we change our SDL flip horizontal to use a ternary operator. Where flip horizontal is true, we pass the SDL flip horizontal flag, otherwise we pass SDL flip none. Now when we run the game, we see that the sprite is flipped in the appropriate direction, dependent on which way we're moving. So far from our sprite sheet, we've only been using the first frame of our animation. But as you can see, there are 8 frames total in our player's idle animation. What we want to do now is build our little animation system. This isn't as hard as it may seem. All we need to do is make sure that we're keeping track of time and advancing through the frames as time moves forward in our game. Let's see how we can do that. I'm going to start off by creating a timer class. We're going to be using this a lot in our game because a lot of things require timers and time tracking. We start off by creating a class called timer, which includes 2 member variables, length and time. Then we create our constructor, which takes a single parameter for length, which we use to initialize our length member variable. We also set time to 0 so that all of our timers start from the beginning. Next, we need to create our step function. This will move our timer forward as our game progresses. Our internal time variable will accumulate time as we add the value of delta time to it frame over frame. Our timer objects will receive delta time from our core game loop when the step function is called from one place or another. When our internal time variable is greater than or equal to length, we have to reset back to the beginning. We don't set time to 0 though, because if we've gone over our length variable by some milliseconds, we would end up losing that time and our internal time tracking would not match the real time. What we do is we subtract length from time, which does almost the same thing, but any amount of milliseconds that our time variable is past our length variable would be left behind, and we would be starting a little bit further forward than we would have if we just reset it back to 0. This way we don't throw away any time and keep our internal game clocks as closely tied to the passage of real time as we can. We're also going to add a timeout variable, which is going to keep track of whether the timer has completed or not. We're going to create a boolean called timeout inside of our class, initialize it to false in our constructor, and once our time reaches our length variable, like we described previously, we're going to set it to true. We also add a member function called isTimeout, which we can then use later on to check if a timer has completed. It simply returns the value of our timeout variable. Let's also add a getter for our time variable, and add a reset function which will set time back to 0 in case we want to start from the absolute beginning. We also can't forget to add a getter for our length because we're going to need that inside of our animation class. Now we can add our animation.h file, and inside there we can begin defining our animation class. First we need to include our timer.h header, and then we can create a member variable called timer inside of our animation class. We also add a variable called frameCount, which will indicate the number of animation frames in a particular animation. First we add a default constructor, which takes no parameters and initializes our timer to 0 length and our frame count to 0. We need this so that later on we can create a vector of animations which can be default constructed without passing any parameters. Now we can create our real constructor, which we're going to use to initialize animations. It will take a frame count and a length. The frame count argument will initialize our internal frame count variable, and the length argument will be forwarded to the timer constructor, which will be initialized inside of our animation object. We also add a getLength function, which simply returns the length value of our timer by forwarding a call to it. One of the more important functions is the currentFrame function. We use it to calculate the current frame of animation that we need to display for our sprite. It does this by taking the timer's time value and dividing it by the timer's length value. This results in a value from 0 to 1, which represents a percentage from the beginning to the end of the animation. Multiplying this by the total frame count will give us the current frame that we should be displaying on screen. We cast the result of this calculation to an integer so that we can drop the decimal place and ensure that the frame number only goes up by whole integers. Finally, we add our step function, which takes in a delta time and just forwards a call to the timer step function. Now we can include animation.h at the top of our main CPP file. Before we move forward and continue loading assets into our game, we need a place to load and unload all of our assets so that we can keep things centralized. We also want to be able to pass around our loaded assets to different functions so that we can change the state of what needs to be drawn. We're going to do that in the simplest way possible in order to keep this tutorial easy to understand. We're going to introduce a structure called resources, which is going to load and unload all of our game assets. It's also going to keep track of all the pointers and integers pointing to different animations, sound files, and textures that we're going to be using throughout our game. Let's start off by adding a player animation to it. We'll create an integer called animPlayerIdle and give it a value of 0. The 0 represents the index of the idle animation, which is going to index into the player's list of animations that we're about to define. We start by including the C++ vector header, and then inside of the resources structure, we define an std vector, we name it playerAnims, and it'll hold all the available player animations that we're going to be defining. Now let's create our load function. This is where we're going to define all the animations, load textures, sound files, music, etc. This function will take our SDLState object by reference, and the first thing we're going to do inside of it is we're going to resize the playerAnims vector for a total of 5 slots. Be sure to call resize instead of reserve because we want to be able to index into this vector. If you call reserve, that'll just allocate memory, but it won't let us actually index into the vector. Once the vector is resized, we can index into it using our animPlayerIdle index and create our idle animation. It'll have 8 frames and it'll run for a total of 1.6 seconds. We can now leave the animations behind for a little while and create a function that will handle the texture loading in a centralized place, which will also keep track of every texture we've loaded in order to clean it up automatically at the end. We start by creating another vector called textures, which will hold SDL texture pointers. Then we create a function called loadTexture, which returns SDL texture pointers. We make sure to include the string header because we're going to pass in a constant string reference, which will represent the file path of the texture we wish to load. Then we're going to take the 2 lines of code from down below, which are the texture loading code we used previously, and change them so they're more generic. We make sure to use file path as the path to the texture and call C_string because SDL being a C API will need to receive a C string instead of an SDL string. Once our texture pointer is created, we push it into our textures array and track it until the program is done. Then we simply return the pointer. Now I'm going to add a member variable which will represent the idle texture so that we can refer to it directly. Then inside of our load function, we try to load it. One thing you probably noticed is we need the SDL renderer to load the texture. So we add that as a parameter to our load texture, and then we pass it from our state object to our load texture function call. Now that we have the groundwork for our loading code, we can add our unload function, which we will end up calling at the end of the program. For now, we're just going to create a for each loop, which goes through all of the textures that we've added, and we call SDL destroy texture, passing the texture pointer and cleaning up after ourselves. Then we can scroll down to the place where we had our texture loading code before, create our resource object, and then call load on it, passing our SDL state. Since we now have our unload function also defined, we can scroll down to the place where we had previously deleted our SDL texture and simply call res.unload, which will trigger all textures to be unloaded. We can also change our render texture rotated function call to take res.textIdle instead of the previous idle text which we had defined. And if we compile and run the application, we'll see that everything still works after the changes that we've made. As most of us know, math and game programming kind of go hand in hand. SDL itself doesn't really offer much of a math library, though it has some rudimentary things that we're going to see later on. What we're going to use is the GLM library. GLM is modeled after GLSL, which is mainly used with OpenGL and Vulkan, but we can use it regardless because it's a great math library and easy to add to our project. I'm going to show 2 ways to add it to the project. You can pick one depending on what you prefer. The first approach is probably easier, but I prefer the second one. What you need to do is download a release from the GLM GitHub releases page, extract it somewhere on your hard drive, Then you're going to create an ext folder inside of the SDL3 demo folder in your project. Then just drag the GLM folder inside of the ext folder. Once that's complete, we can add a target include directories call into our CMake list file, setting SDL3 as the target, private, and adding ext/ as one of the search paths for our project. Once you save and reconfigure CMake, we can head back to our main file and try to include the glm/glm.hpp header to make sure that we set up everything. We can also further verify that things are where they need to be by trying to create a 2D vector from the GLM namespace and compiling our code. That's one way to add GLM to your project, but I prefer to stick to CMake with everything. So what I'm going to show you how to do is to actually build the library from source and install it on our system so that we can use find package with it. I prefer this because it means I check in less files into my Git repository and I keep dependencies out of my source tree. We start by downloading the source code package. Then we open our command prompt or terminal of our choice and we cd into that directory. Then we just need to run CMake to configure a build for GLM. And even looking at the GLM Git repo, we can see some instructions on how to speed up our build. In this case, we want to disable the building of the tests as well as the shared library. The compilation of the tests for GLM take forever, so we don't want to do it. We run CMake-s and then the location for the CMake list file, and then -b specifying the build directory name we wish to create. Then we follow up with a pair of -ds so that we can configure two parameters for the build, turning off the tests as well as the shared libs. Running this command will generate the build files for us and allow us to compile GLM. Then we just run CMake-build and then specify the build directory. And if you're using Visual Studio like me, you can do --config space and release for a release build. Then all we have to do is run CMake again, --install, specifying the build directory, once again specifying the release configuration, and --prefix, specifying the prefix for where we want to install GLM. This will install a CMake-friendly installed version of GLM, which we can then find using find package. Be sure to copy that prefix path to your clipboard because we're going to tell CMake where to find GLM right now. Heading back to our CMake user presets.json file, we add the GLM path we just copied to the end of the list, fix the slashes, be sure to save, and then head over to our CMake list file so that we can add another find package command for GLM. Once you've done that, you can go to the line that says target link libraries and add GLM::GLM, and now we're ready to roll. Let's continue by adding a new file to our project. We'll call it gameObject.h. The struct that we're going to be defining will represent every single object in the game, whether it's the player, any level tiles, background, foreground, or enemies. We include the GLM header since we're going to be using the vector2 type. We add an enumeration called object type, which we're going to use to differentiate the different types of objects in the game. Then we can define our gameObject struct. The first field that we give it is the object type field, and then we can create our default constructor which initializes the gameObject to a level type. Then we create three 2D vectors, position, velocity, and acceleration. We're going to be using these to move the player around shortly. We also need a direction field, and then we initialize direction to 1, and our position, velocity, and acceleration vectors to 0. Our direction field is going to dictate whether the player is going left or right, and it's going to hold a value of 1 or -1, -1 being left and 1 being right. Each object is also going to have a vector of all of the animations that it's using, as well as an integer which will be the current index of the animation we're displaying on screen. We add an std vector of animation objects, as well as our integer representing the current animation, and we make sure to initialize current animation to -1, which we'll use to signify no animation at the moment. We also include the SDL header because we want to create a pointer to an SDL texture as part of our gameObject. This will tell our drawing code which texture we want to draw from. With our gameObject set up, we can go back to our SDL3 main code and replace the include for animation.h with the include for gameObject.h. That's because gameObject.h already includes the animation header. Now we can start creating a structure that will hold the actual game state. This will hold everything from gameObject, the player, any enemies that are roaming around, bullets on the screen, things like that. We're going to take the approach of splitting our objects into layers. This way we can set some order in which we draw things. We're going to have an std array of vectors which are going to be themselves arrays of gameObjects. This is because we're going to know how many different layers we have, but we won't know how many different game objects we have. An STD array is perfect for when you have a finite number of things, and an STD vector is when you have a dynamic number of things. We start by including the array header, and then we'll define a couple of constants representing indices to the various layers in our game. Once we've done that, we can add a field called layers, which is going to be our STD array of STD vectors of GameObject. And our STD array is going to have 2 elements. We also add an integer called player index, which we'll use to cache the index of the player GameObject within the characters layer. This is so that later we can refer to the player directly without having to search for it every single time. For now, we can set it to 0 because that's going to be the only object in our game. Later, when we start loading the map, you'll see why this is useful. Let's now create a function that we can use to draw any of the objects we're going to be adding into our game. Scroll down to the bottom of the file and create a function called drawObject. It's going to take our SDLState by const reference, our GameState by reference, and a GameObject by reference, and also our delta time. Then go up to the code that we had previously used to draw the sprite and move it inside of this function. Inside of the destination rect, change them to use the object's position x and y values. Then create a variable called flip mode of type SDL flip mode, which is going to use a ternary operator to check if direction is -1, in which case it uses SDL flip horizontal, otherwise it uses SDL flip none. Then we provide that variable to our render texture rotated call, and we tell it to use our object's texture pointer. Copy the signature of our new function and paste it underneath the other forward declarations at the top of our file. Then select all the function declarations and paste them just above our main function. We want them there because they're referring to types that are declared above them. Let's head down to the setup game data section and create an instance of our GameState object. Delete the declarations for player x, floor, and the flip horizontal boolean because we're not going to be using those anymore. Now we can create an instance of our GameObject class to make our player. Set the object's type to object type player. Set its texture to res.textIdle. And give it a copy of the animations that we had previously stored inside player anims. Every object in the game needs its own copy of the animations so that it can manage time separately and independently from other objects. What we do when we create new objects is we give them a copy of the animations appropriate for their object type, in this case, the player object. This is obviously required since if we didn't do this, every enemy in the game would be playing the exact same animation at the exact same time and frame at all times. Of course, that would look horrible considering every enemy would be responding to a different thing at any given time. To wrap this up, set the current animation to the anim player idle index, and then push the player object into our characters layer. Now we can head back down to the section after clearing the screen, and we can iterate through our layers, and inside of each layer, we can iterate through all the objects. We can call our drawObject function, passing in our SDLState, our GameState, our object, and the delta time. Calling this will handle the drawing for any object we have in the game going forward. Let's also remove the old input handling code because we don't need that anymore. We're going to be handling player movement and input in a much better way going forward. Now that we have our timers, animations, and game objects all tied together, we can create the block of code that's going to be updating our game objects. It's going to be another set of for loops, just like the drawing code below, but here we're going to handle any updates that need to happen to the game objects before they're drawn. For the moment, we're only going to check if the current animation value is not equal to -1, and if it's not, we're going to use it to index into the object's animations array and call step on the current animation. We're providing the delta time that we computed in our game loop, and this bit of code here is what actually ties the core game loop to our animation system. To actually see this working, let's head down to the drawObject function and change the source rect structure so that it's not always referring to 0, 0 for the x and y values. What we're going to do is we're going to create a variable called sourceX. It's going to check if there's a current animation, and if there is, it's going to compute the x value to be the frame number, which is a 0-based index of the frame, and multiply that by the sprite width. So for example, the first frame is going to be 0 times 32, the second frame is going to be 1 times 32, the third frame is going to be 2 times 32, meaning 64, so it's going to start at a different X position within our sprite sheet. This way, as the animation moves forward, our current frame value goes up, and this source X value will represent a different starting X position within the sprite sheet. Eventually, we're going to implement things in a way where we're loading a data file where each frame corresponds to a particular portion of a texture. This way, we can be much more efficient about how we pack things. We can have more than one animation per texture, and so on and so forth. We can still use the same animation system, except in our future approach, we're not going to be calculating an X value, but rather we're going to use our frame number to index into a data structure that associates each frame of an animation with a portion of a sprite atlas. With all that said though, the current approach is going to serve us quite well for the time being and doesn't need upgrading just yet. So far, we've only checked if the user is pressing the A and D keys to move left and right. But as we continue to add features like jumping and shooting, our code can quickly become very unmanageable. What normally happens is you end up with a whole bunch of nested if conditions, checking all kinds of different gameplay state, just to figure out what state any given entity in the game is currently in. As you can imagine, our player will have a set of states that they'll be able to be in, such as idle, jumping, running, etc. Different enemies will have their own different set of states, and any other interactable item or entity in the game will have its own set of states. If we don't manage things in a clean way, you can end up with very complicated code that becomes very cumbersome and error-prone to manage, ending up with all kinds of little bugs all over the place, which just leads to frustration. What we're going to use is what are called finite state machines. This is really just a fancy name for keeping track of the current entity's state, and also writing our code in a way where any entity in the game can go from one state to a fixed number of other states given a particular condition. What I mean by this is, if for example we're in the idle state, we can press a button to go to the jumping state, or press left or right to go to the running state. We can also press another button to go into the crouching state. The reason we can do these things is because we know that if we're currently in the idle state, we should be checking for those button presses. But if we're in the jumping state, we're just not going to check if the user's holding the crouch key, and we could never transition from jumping to crouching since you can't crouch in midair. Let's start writing some of the code to handle all of this, and it will become much more clear why we're doing it and what it actually entails. There are many different ways to implement a finite state machine, but really at its core, it's really just about managing state and its transitions. We're going to create an enumeration called player state, which we're going to use to keep track of the player's current state. We're also going to have equivalent enumerations for every other type of entity in our game. We're going to have a bullet state, an enemy state, and so on as we add more things to our game. Currently, we're just going to focus on the player. A lot of developers opt into complicated object-oriented hierarchies in order to manage the various states in their games, but really you just need some way to track the current state and also know when you're transitioning from one state to another. Also, using an enumeration makes it easier for me to demonstrate how this actually works. If I had to jump around a whole bunch of different classes and override virtual methods, we could quickly get bogged down in the architecture of things rather than demonstrating the core concept itself. Now that we have our player state, let's create a structure called player data, which will have a member variable called state, which is going to be of type player state. This player data structure will be used to keep track of any state that pertains only to the player. We're also going to create a constructor for our player data structure, which will make sure that whenever we start the game, our player state always starts at idle. We can have equivalent data structures for level tiles, such as flooring and walls, as well as enemies, bullets, and any other types that we want to add into our game. Then in order to have a generic data field in our GameObject, we're going to create a union between those different data structures, and we're going to create a data field inside of our GameObject that will let us get at the different data structures depending on the type of the GameObject. What a union does is it allows you to create a structure of overlapping data types inside of it. So the player data, level data, and enemy data all overlap each other in memory, and you can only use one of those fields at any given time. So anytime we want to access data, first we check the type of our GameObject, and then we can access the appropriate data structure inside of it. To finish setting this up, I'm going to create a structure for our level data, which we could use to store level-specific data. And then I'm going to have another structure for enemy data, which will be for our enemies that we're going to be adding later on. Then we add two other fields to our union, one called level and one enemy, and now we have the overlapping data structure. The last thing I want to do is initialize our data union to the level data structure, This way it's initialized to level like everything else that we've done so far in the GameObject. Let's head back to our main source file and go all the way to the bottom underneath the drawObject function. We're going to add another function with a very similar signature called update. Once again, it takes our SDLState by const reference, our GameState by reference, resources by reference, our GameObject by reference, and our delta time. In here, we'll check what kind of object we're updating. In this case, we're checking if it's the player object. And now we can re-add some of the input handling. What we're going to do is we're going to go up to our SDLState structure and we're going to add a field for our keys. It's going to be a const pointer to a Boolean array, which has to be initialized inside of our constructor's initializer list. We initialize keys to SDL get keyboard state, passing null pointer as an argument. Then let's scroll down and delete the previous call to SDL get keyboard state, since we're not going to be using that one anymore. Back inside our update function, in our player update block, let's create a float variable called currentDir and initialize it to 0. Then we check if the user is holding the A key or trying to go left, and we add -1 into that variable. After that, we check if the user is holding the D key, and if so, we add 1 to that variable. It's important to note that we're adding 1 and removing 1 to make sure that if both keys are pressed, currentDir will result in a 0 for that frame. Immediately after those two if blocks, we check if currentDir is not 0, and if it's not, we change the current GameObject's direction to the one we just computed. This makes sure that the GameObject's direction is always up to date. Now we're going to create a switch block based on the object's data.player.state property. As you recall, in order to get at player-specific data, we have to go into the GameObject, its data field, and once we know that we're working with a player, we can do .player and then access any player-specific properties. And it's inside this switch block here that we can start defining our state-specific logic. Let's add a case for our idle state and our running state. Looking at our idle state, we know that if a player is holding a direction, then they should transition to the running state. So what we do is we check if current direction is not 0, meaning a direction is being held, in which case we go inside the player data structure and change the player state to running. Inside of our running case, we do the opposite. We check if current direction is 0, and if it is, we change the player state to idle. And since this update function is called repeatedly for every iteration of our game loop, this state is constantly changing back and forth as the user is moving the player left and right. We also need to add a field to our GameObject called maxSpeedX and make sure we initialize it to 0 in our constructor. This variable will let us give each individual object a maximum velocity in the x-axis to ensure that objects don't have infinite acceleration. Now we can head over to the bottom of our update function and add acceleration to our velocity. We take the object's acceleration and multiply it by current direction and the delta time. This gives us the acceleration per frame, which we add to our velocity vector, which tells us how fast and in what direction our object is traveling. After that, we take the current object's velocity, multiply it by delta time to get the velocity per frame, and add that to our player's position. This is what ends up moving our sprite along the screen. We need to remember to give our player some acceleration value, which will tell the game how fast the player can reach maximum speed, and we can't forget to set a maximum speed in the x-axis, otherwise it'll just be 0 and our player won't go anywhere. I'm using 300 for the x-axis acceleration and setting a max speed of 100, but these values are mostly arbitrary and I just like the way they look. Now we can take our update function signature and declare it at the top of our main file so that our code can see it. Now let's scroll down to the two loops where we update our objects and make sure that we call update for every object in every layer. If we now run the game, we see that our player is moving using the acceleration that we've set. The only problem is that we're not limiting the speed in the x-axis, which we're going to do now. We need to check if the absolute value of our velocity in the x-axis is greater than our max speed x value, and in the case that it is, we set our velocity's x value to the current direction times our maximum speed x. This will clamp our velocity in the x-axis to the max speed and retain our direction. Now that our player can start moving properly, we need to make sure that he can actually stop moving. So we head over to our update code, and in the case that our player is idle, we need to add some code to decelerate and make sure that our player can come to a stop. The way we do that is we check if there's currently velocity in the x-axis, and if there is, we create a deceleration factor, which lets us slow down faster than we speed up. If our velocity is positive, we use a negative deceleration factor of 1.5. If it's negative, we use a positive 1.5. Then we take our factor and we multiply it by our acceleration's x value, and then times our delta time. This gives us an amount of deceleration that is inverse of our acceleration and slightly faster. If the absolute value of our current x velocity is less than the absolute value of this deceleration amount, we just set velocity x to 0 to make sure the player comes to a complete stop, since we can't decelerate any further. Otherwise, we add this value to our x velocity, which will be a force that is inverse to our current x velocity, causing us to slow down. Even with that code in place though, we're still not slowing down. This is because we haven't set the data property of our player object, and the state value isn't actually initialized to anything, and our union has a bunch of junk data. What we need to do is set player.data.player, which is the player data value inside of the union, to an object of player data. This will initialize it using the constructor that we set up earlier. This constructor sets the initial value of our state variable to idle, which ensures that we don't have junk data in our state variable. With our player moving left and right correctly, it's time to add the running animation so that we can actually make this look nicer. Going to our resources struct, let's add an animation for our player running. This one's going to have an index of 1. We also need to add the running texture and load it, just like we did before. Now let's head over to the code that switches into the running state and set our player texture to running, and set the current animation to the new running animation we just defined. Down in the block where we switch from running to idle, we do the opposite. We switch the texture to idle, and we set the current animation to our idle animation. Now when our player transitions between these two states, it'll switch to the appropriate animation. This was very easy because we already have the setup for our animation system and our state management. Moving forward, we'll be able to iterate much quicker because everything's in place for our gameplay systems. We've got this player that's able to walk left and right and animate in and out of different states, but there's nothing to actually walk on. Let's set up a rudimentary map loading system, something that doesn't require us to load and parse different data files, so we're just going to use a 2D array to define the different types of tiles that make up our level. Let's see how that's done. We'll start by defining some constants at the top. We'll have 5 map rows, 50 columns, and a fixed tile size of 32. This will make our map 250 tiles at 32 by 32 each. Then let's head down to the bottom of the file and create a function called createTiles. It'll take our standard parameters, SDLState, GameState, and our resources. Let's now create a 2D array called map, which is going to be map rows by map columns in size. Then let's create 5 rows of 50 zeros, just like I'm doing on screen right now. The zeros represent empty tiles. If we replace the 0 with a 1, 2, 3, 4, 5, or 6, that'll represent a tile of the type that you see on screen right now. I'm setting our player at row 3, column 1, which means that when the map loads, we're going to calculate what pixel location our player is supposed to be at, given their row and column within the tile map. First, we loop through all of the map rows. We create a for loop that goes from 0 to map rows. Inside of that, we loop through all of the columns. This way, we iterate through all of the tiles horizontally and vertically. Inside of the inner loop, we create a switch. The switch is based on the current tile by indexing using the R and C variables from our for loops. With that set up, we can create cases for every single type of tile that we'll be implementing. Let's start with the case 4, which represents our player. If we scroll up to the code where we create our player object, let's cut it from there and paste it inside of case 4, because instead of just creating the player outright at the beginning of our program, we're now going to create the player at the appropriate position based on its row and column inside of our tile map. And just like the rest of our functions, we need to take the function signature and put it at the top so that we can actually call it further in our code. Then we go to our setup game data section and we call createTiles after we create our GameState object. Back to our player creation code, let's create a GLM vec2 and store that in position. This is going to dictate the X and Y value of our tile. The way we calculate the tile's position is as follows. The column is easy. We just multiply the C value times tile size, which gives us the horizontal position of each tile. The vertical position is a little trickier. We want to make sure that our tile map is flush at the bottom of our logical resolution. We don't want a gap between our level and the bottom of the screen. So what we do is we subtract the vertical position of each tile from the logical height resolution. But if we do this directly, we just get an inverted tile map. And that would result in all tiles in the first row being at the bottom of the screen, tiles at the second row being one row up from the bottom of the screen, and so on. Essentially, our y-axis flips. We don't want to do that. So what we do is we also invert our r value. We take our map rows, we subtract r from it, so our 0 would become a 5, our 1 would become a 4, and so on. Then we multiply that by tile size, and then we subtract that from our logical height. This results in the tiles being drawn in the right order from top to bottom and placed flush at the bottom of our logical resolution. Earlier when we wrote our drawObject function, we didn't specify a y position for our destination rect. Let's go back there and set the y position to the object's y position. Now when we run the game, we'll see the object placed accordingly. Now we can easily go to the tile map and set the position of our player just by changing the position of our 4. I've placed the player in the bottom row, and now the sprite is being drawn at the bottom of the screen as expected. With our tile system in place, let's add a few more tile types to give our level some variety. I'm adding a panel, dirt, grass, and brick textures so that we have something to work with. We start by adding the SDL texture pointers to our resources struct so that we can refer to these textures, and then we call load texture like before to get them loaded into GPU memory. Now we head back to our create tiles function. We're going to make a lambda called createObject. It's going to capture our state, and it's going to take the row, column, an SDL texture, and an object type as arguments. Inside there, we're going to create our GameObject, set its type. We're going to move the position calculation in here so that every tile can use it. Then we set the texture to the one that's passed in, and we return this object from the lambda. C++ move semantics will guarantee that we're not copying the object out, but rather moving it. Then inside of our player case, we're going to call createObject, passing the required arguments, and an object type of player to create a player object. We can also remove the lines that set the type and texture on the player in this block because our createObject lambda does that for us. I'm going to quickly add a few ground tiles to our tile map and move our player up so that we have something to land on and use as a walkable area. Now we're going to create a case handler for the value 1, which is a ground tile. And then we call our createObject lambda, passing in the row, column, the ground texture, as well as providing an object type of level. Then we just add the new object to our level layer. And if we run our game, we see that the tiles are visible. Great, let's add a panel tile. All we have to do is copy the code that creates our ground tile, change the case value to 2, and set the texture to the panel texture. Simple as that. Let's also add a few panels to our map and extend our walking area. That's how easy it is to add new types of tiles with our setup. When we run the game, of course, we see that we're just floating above our level and nothing's really happening. Let's add some gravity. At the top of our update function, we're going to create a glmvec2 with a y value of 500, and then we're going to scale the whole vector using our delta time. This will give us a downward force per frame, which will represent our gravity. Then we just add it to our object's velocity, and we have our gravity. Now at the bottom of our update function, let's take the code that changes the object's position out of the ifPlayer block and put it right at the bottom so that objects of all types can use it. But this actually affects all of our tiles, including our level tiles. So we're going to go to our GameObject and we're going to add a boolean called dynamic and default it to false so that objects are not dynamic by default. Then we're just going to surround our gravity code with an if dynamic check. And since our level tiles are not dynamic by default, they won't get pushed down by gravity. All that's left to do is to go back to our player and make sure that our player object is dynamic by default. Great, now we can control which types of objects receive gravity, but we're still just falling through our level. So let's look at how we're going to handle some collision detection. Let's add a function above our createTiles function called checkCollision. It's going to receive the usual suspects: state, GameState, resources, and here we're going to have GameObject A and GameObject B. All of this passed in by reference, and of course our delta time. We're going to create two objects of type SDLFRect, Rect A and Rect B. The X and Y values are going to be based on the object's position, and the width and height values are going to be our default tile size, which is 32. These rects will represent the hitboxes or collision boxes that we're going to be using to check if two game objects are intersecting one another. we use Rect C to tell us how far the two objects are overlapping. Once we have Rect C, we know how far object A is overlapping object B. The overlap in the x-axis is represented by the width of Rect C, and the overlap in the y-axis is represented by the height. Then we can simply call SDL_getRectIntersectionFloat, passing in our A collision box, our B collision box, and our Rect C, which will give us the result of the intersection. If this function returns true, then we know that we have an intersection. In this case, we're going to make our next call, which is our collision response function. It's going to have almost the same parameters as check collision, with the inclusion of Rect A, Rect B, and Rect C, which we're going to use to resolve our collisions. Once we call collision response with the appropriate arguments, we're telling our game that two objects have collided. So inside of our collision response function, we first check what object A is. In the case where object A's type is player, we're going to check what our player is colliding with. We add an outside if for objects A and an inner switch for the various objects that we're colliding with. We're going to add a switch case for the level tile. In the case where our player collides with an object vertically, we see that the height of Rect C would be much less than the width. So in order to resolve that collision, we just have to nudge the player up by the height of Rect C. In the case of a horizontal collision, it's the opposite. The width is much lower than the height, so we nudge the player in the horizontal axis based on the width of Rect C. First we check if the width of Rect C is less than its height, in which case we know that it's a horizontal collision. In the else case, it's a vertical collision. In the case of a horizontal collision, we first check if velocity x is greater than 0. In the case that it is, that means that we're traveling towards the right, so the object we're colliding with must be to the right of us. And in this case, to resolve the collision, we subtract the width of Rect C from object A's x position. If we're going in the opposite direction and hitting an object to our left, then we add the width, nudging the object to the right. And since this is a collision in the horizontal axis, we set the x velocity of object A to 0 in order to stop it from moving. Collisions in the vertical axis are handled the exact same way. If y velocity is positive, then we must be moving downwards and hitting an object below us. If that's the case, we nudge the object upwards by subtracting the height of Rect C from the object's y position. In the case the y velocity is negative, then we must be moving upwards and resolve the collision by nudging the object downwards. And just like in the horizontal axis, we set the velocity for this axis to 0 to stop the object from moving further. In case you haven't caught it, we can't just leave our velocity checks with an if followed by an else. We need to actually have an else if to check if velocity is first positive and then negative. Simply having an else means that it'll first check if that axis is positive, and then if it's 0 or negative. In the case of a 0 velocity, we don't want to actually respond, so we need to have an else if and check if it's negative. Then once we find a collision, it's just a matter of calling collision response and passing the appropriate arguments. Now we declare check collision at the top so that we can actually call it and move down to our update function. A quick reminder that this code gets called for every object in our scene. What we're going to do is for every object in the scene, we're going to check it for collisions with every other object in the scene. And we make sure that we're not checking objects with themselves by comparing memory addresses. The current call to update would give us our object, and the nested loop would give us object B. Then we simply compare their memory addresses, and if they don't match, we call check collisions between the two. This approach of checking every object against every other object is not efficient at all, but we're going to run with it for now because it's simple, and later on we can come back here and optimize away all the unnecessary collision checks. Now when we run the game, we don't fall through the floor, and when we try walking towards the right, we're blocked by our panel tiles. Let's change up our level so that we spawn on top of the panels and see what happens when we try walking towards the left. This illuminates an issue that makes our game look kind of bad. Our sprite tiles are 32 by 32, but the actual pixels that represent our character sprite don't fill that space entirely. So if our collision detection has a bounding box of 32 by 32, we end up looking like we're floating through the air until our collision box is no longer colliding with the ground beneath it. We can easily solve this problem by giving ourselves the ability to provide custom dimensions for the portion of our sprite that can collide with other tiles. For this purpose, we're going to add a collider rect. It defines x and y coordinates relative to the top left of our tile, as well as a width and height that represent the collidable area of our sprite. This provides a lot more control over which part of the sprite is actually collidable with other tiles. So what we do is we add an SDL Rect to our GameObject struct, and we initialize it to 0. This will result in GameObjects not actually colliding with anything if left to their default values. And now inside our check collision function, we have to reflect the collider size in both Rect A and Rect B. We add the x and y values of the colliders to the position values, and for the width and height, we use the collider's width and height. This will ensure that the custom dimensions of our colliders are taken into account when doing our collision detection. Heading over to our player creation code, we have to make sure that we provide a collider size for our player so that it defines a hitbox that can collide with other objects. I tried a few different values and I like these ones for this current sprite. I'm also going to head over to our createObject Lambda and set a default collider for anything that it produces, which is going to have 0, 0 for the x and y offsets and tile size for both width and height. This ensures that all the variations of our level tiles will have a default collider and we won't have to set this up for each one. Now if we run the game, we see that our sprite has a much narrower hitbox and it interacts much nicer with our level tiles. So now that we can move and interact with the environment, let's see if we can add some jumping so we can get back up those boxes. Let's add a function called handleKeyInput, which will have our state, GameState, and a GameObject. It will also receive an SDL scan code, which represents a key on our physical keyboard. The last parameter is a boolean, which states whether the key in question is being pressed or being released. After adding the function declaration at the top, let's head over to our event loop and add a couple of events. We're going to add SDL event key down and SDL event key up, each of which representing whether a key is being pressed or released. What we want to do is capture these events and forward them to our player. This will let our player respond to specific key presses, which is different than what we were doing in the update function where we check whether the A or D key are being held. The previous method is great for continuous input, such as walking or holding the shoot button, but this one is important for when we want to handle a key up or a key down event specifically, such as jumping. So what we want to do is call handleKeyInput for every time we have a key down or a key up event and forward it so that we can do something with our player object. But we don't actually have easy access to our player object. If you recall, in our GameState constructor, we set player index to 0. Let's set that to -1, which is going to represent none. And then inside of our player creation case, inside createTiles, we're going to cache the index of the object that represents our newly created player so that we can refer to it down the road. And then at the bottom of our tile creation loops, I'm going to put an assertion to make sure the player index is not -1. If it's -1 at this point, that means that there was no player set in our tile map represented by the value 4, which obviously means that we can't play our game. We're also going to add a method called player inside of our GameState struct, which is going to directly return the object pointed to by player index. At the point at which we call this function, we would have a player index because the map would be loaded and we would be able to directly get our player object without having to look for it. So now when we call handleKeyInput, we can just call the player function on our GameState object and directly get a game object that represents our player. We also get the current scan code by accessing the SDL event.key.scanCode, and for the last event, we pass true on key down and false on key up. And just to demonstrate things, if we remove the player from our tile map and run the game, the application crashes and we see the assertion that triggered the crash in the console. This is our player index not equal to -1 assert call. With everything in place now, we can start writing the code that will make our player jump. The first thing we do in handleKeyInput is we check if the object type is player. We know it's going to be player because we're passing the player object directly, but we do this anyways because down the road we might want other objects to support key input. Then inside of our if block, we add a switch for the current state of the player. We check if the key that's currently being pressed is K, which is going to be our jump key, and that it's actually pressed down. If that's the case, we want to apply a jumping force to our player velocity. First, we're going to define a constant for our jump force. This is going to be a value of -200 to represent an immediate upward force. So then when we actually trigger a jump, we add this value to our player's y velocity, and we make sure to change the player state to jumping. We're also going to duplicate this code inside of our running state to make sure that we can jump while we're running. Let's not forget to put the player back on our map, and then we can run the game and try our jumping. If I press the K key, our player jumps up, but now seems to be stuck in some state where I can't jump and the running animation doesn't play. Let's see what's going on. This is a good time to show how we can display some useful information that can help us debug problems with our gameplay. We're going to display some basic text on the screen, so we're going to head down to our code right before our render present, and we're going to call a couple of functions. First, we call SDL set render draw color, passing in our renderer, and 255 for all color components for pure white. Then we call SDL render debug text, again passing our renderer, passing a 5 and then a 5 for the x and y coordinates, and then the text that we want to display on the screen. The text is going to be in the top left at the position that we specified. Now that we know how to display text, let's actually display something useful. First, let's include the C++ format header from the standard library. You don't have to use std format, you can use sprintf instead, but since I like C++, I'm going to stick to the standard library. Now back to our SDL render debug text call, we can call std format, passing our format string, where the curly braces represent the placeholder for a value. After the format string, I'm going to pass the values that need to be inserted. In this case, it's our current player state. We can't just display it like this directly though, because it's a C++ enum. What we do is we cast it to an integer, and then the named values will get converted to numbers as follows. It's simply a matter of wrapping it with a static cast and using an integer as the type. Then we can just call cstring on the result of our std format call, and we're good to go. Now we have an easy way of displaying our current player state on screen. What we see now though is when we jump, we get stuck in state 2, which is our jumping state. This is because we have a way of getting into the jumping state, but we have no way of getting out of it. Currently, we're going from idle to running and from running to idle. We're also going from either of those states into our jumping state when we press the K key. What we need to do is check when the player lands on the ground and then switch them back to the running state. If the player is no longer holding the A or D keys, then they would immediately get switched back to the idle state on the next frame. We're going to start by adding another boolean to our GameObject called grounded. We also make sure that it's initialized to false in the constructor. This will tell us if the current object is standing on the ground. Then we're going to head down to our collision detection code, right underneath where we call check collision on our objects, and we're going to add another SDL frect called sensor. This collision box will be underneath our player in 1 pixel in height. Its x position is going to be the same as our player collider's x position, but its y position is going to be placed underneath our player. We get this value by adding the current player's position plus the collider y value and the collider height value. This will put it right underneath our player. Then we set the width to the collider, just like the regular collision detection, but we set the height to just a single pixel. When this rect intersects any object underneath our player, we'll know that the player has landed on the ground. Let's add a boolean above our for loops called foundGround and initialize it to false. Then after creating our sensor rect, let's create another rect called rectB, which is going to represent the bounding box of the object that we're checking against, just like our regular collision detection. Now with those rects set up, we can call SDL has rect intersection float, passing in the sensor, and rectB. This function returns true in the case of a collision, and when there is one, we set foundGround to true. I'd like to quickly point out that has rect intersection and get rect intersection seem to return different results. And later on, we're actually going to switch to using get rect intersection. So if you notice any issues as you're jumping around, just ignore them for now. We're going to resolve that later on. At the end of all of our collision checking, we compare the current object's grounded value with the value inside of foundGround. If they don't match, that means we're changing state, either going from grounded to airborne or vice versa. We first want to update the current object's grounded state with the value of foundGround. And then, if we're actually grounded, we check if the current object's type is player, and if it is, we change the player state to running. With this in place, we're no longer stuck in a jumping state, and we can hop around all we want. There are a couple of issues here though. First, we don't want to be in the idle animation while we're jumping. Second, we don't seem to be switching between our player's animations correctly. This is because in our current setup, we're expected to change texture and animation every time we change state. This will get buggy and it won't work very well with what we're going to do further in. So what I'm going to do is go back to our update function, and then inside of our player state cases, I'm going to make sure that each case sets its texture and animation correctly. So instead of just changing textures and animations when transitioning states, we're going to make sure that each state sets its texture and animation correctly. Inside of the running case, we set the running animation and texture, and inside of the idle case, we set the idle animation and texture. Now we just need to add a case for our jumping state, and we're going to reuse our running animation. If we now run the game and start hopping around, we see that our player is animated better, and when we jump around, his feet are wailing around, which looks a lot better than him standing still. After a little bit of code documentation, let's make our movement even nicer. We're going to change our animation and texture when we're sliding after starting to walk in one direction while we're still moving in the other. All we have to do is check if the sign of our current x velocity is different than the sign of our current direction. The way we do that is by multiplying velocity x by the object's direction. If the result is negative, that means that the two have different signs. This is because a positive times a positive is a positive, and a negative times a negative is also a positive. The only time the result is negative is when the signs are different. And of course, we don't want to slide unless we're actually on the ground. We're going to set up an else case for the regular running animation, and inside the if block, we're going to set up our sliding animation. Let's go back to our resources, set up a pointer for our sliding texture, load it, we also need an animation index for our new sliding animation, and we just need to define it. This isn't really an animation at all, it's just a single frame that holds for 1 second. I'm only doing this because we always require an animation with our current setup, but later on we can change that. Now back inside our if block, if we establish that we're supposed to be sliding, we set the sliding texture and the sliding animation. Now if we're running in one direction and quickly switch to the other while we're decelerating, we'll see that our player is sliding and facing the other way, which looks a lot nicer. Let's head over to our create tiles function and expand our map so we have more of an area to walk on. We're going to also add a bunch more panel tiles so there are more places to jump around on. As we're walking around, you see that we can walk off of the map and the camera doesn't follow our player. This is because there is no camera. We have to build something into our game that resembles a camera and follows our player along the map. What we're going to do is establish a notion of a map viewport. This is going to be the portion of map that we're currently viewing based on the player's position. We're going to head over to our GameState struct and we're going to add an SDL Rect called map viewport. This is going to be the rectangular region that we're currently viewing as the player. We're going to also pass in our SDL state by const reference to our GameState constructor. This way we can initialize our map viewport with an x value of 0, a y value of 0, and a width and height set to match our logical resolution. We also need to cast the logical width and height from an int to a float since we're using an SDL Rect to keep track of our map viewport. Now let's head down to our game setup code and make sure we pass our SDLState object to the GameState constructor. What we want to do now is write some code that'll keep the player centered in the middle of our screen, while at the same time giving the illusion that we're scrolling through the map. We're not actually scrolling or panning a camera. What we're actually doing is getting the player's current X position, adding to it half of our tile size, so that would be 16, which would give us a coordinate that is at the center of our sprite, and then subtracting from that 1/2 of our map viewport's width. This results in an X coordinate that's based on the player's current X position, but offset just enough to place the player in the middle of the viewport. If we then subtract the map viewport's X coordinate from every object when we draw, then we're going to get the illusion that everything is moving around our player while our player is in the middle of the screen. We perform this calculation just before we start drawing and after we do all the object updates. This ensures that our viewport is based on the latest player position. All we have to do now is head over to our drawObject function, and in the destination rect, for the x value, we just subtract mapViewport.x. This will offset everything as we draw and make it look like we're panning across our game level. Okay, so now that we can walk around our map, let's make things look even better by introducing a few different backgrounds. We're going to have one static background that's always going to be still, as well as 3 other ones that are going to make up 3 layers of a parallax background. Parallax simply means that the different layers are moving across at different speeds, giving the illusion of distance. Each layer of the parallax effect will be a seemingly different distance from our camera. We're going to need to add 4 new pointers to our resources structure, which are going to represent each background layer. Text BG1 will be our static background, and text BG2 to 4 are going to make up the 3 layers of our parallax background. Then we just have to load them as usual, and we can start drawing them. The first layer that we're going to draw is BG text 1, and we're not going to pass any source or destination rects because we're drawing the whole texture to the whole screen. We don't need any specifics here. When we run the game, we see that the background is drawn first, and then we're drawing all of the game tiles on top. It's already looking better, but once we add the parallax effect, it's going to look much cooler. We're going to add a function called drawParallaxBackground, which will take our renderer so that we can actually draw with it, a texture, which is going to represent the parallax layer, the current x velocity of our player, a scroll position by reference so that we can actually change the value in the variable, a scroll factor which will let us control the speed of each individual layer's scrolling speed, and our delta time. Then what we do is we take the scroll position and we subtract from it the x velocity times the scroll factor times the delta time. What this subtraction does is it moves the scroll position in the inverse direction from our player, scaled by the scroll factor. If the scroll position reaches a value that's less than or equal to the negative texture width, we just reset the value back to 0. So what ends up happening is as our player is walking towards the right, our background is moving towards the left at a speed that's relative to our player movement speed, but scaled by our scroll factor. And once the background goes far enough to the left, we just snap it back at 0, which is its original position. The way we avoid seeing a gap on the right side of the screen as we move the background to the left is by drawing the background twice, once in its original position and a second time off screen directly to the right. Then as the background moves to the left, the second tiled copy also moves in from the right side of the screen and we never see a gap. And once the first copy has completely exited the screen, we snap the whole thing back and the player never notices. The easiest way for us to tile this texture across twice is to use the SDL render texture tiled function. When you provide a destination rect to this function, you can scale the value of the width or height depending on how you want to tile your texture. In this case, we're setting the width to 2 times the texture's original width because we want to tile twice in the x-axis. And when we call this function to draw the texture, we'll essentially get 2 copies along the x-axis. This also eliminates the need to call render twice, since we're getting 2 copies with a single draw. And as usual, we want to declare this function at the top so we can call it, and head over to our GameState struct so we can add a few variables. We're going to add a few floating point variables that are going to hold the different scrolling positions for our parallax layers. Then we initialize them all to 0, and we can start drawing. All that's left to do now is to call drawParallaxBackground, providing our renderer and the textures that we want to draw. The first parallax layer that we're going to draw is text BG2. We're also going to use BG2 scroll as a scroll position and 0.3 as the scroll factor. If we run a quick test, we see that the background is now drawn, but we want to nudge it down a little bit to remove that bar at the bottom. So I'm going to head over to drawParallaxBackground and set the Y position to a larger value, which will fix it. If we run the game now, we see that it looks better. Okay, so now we can draw the other layers of our parallax background. Since we're drawing the layers one on top of the other, we start with text BG4 being the furthest, and then we draw text BG3 and then text BG2. Be sure to match each texture layer with the appropriate scroll position variable based on the number. As for the scroll factor, the layer closest to us will start at 0.3, which will cause it to move the fastest. Then when we go to draw layers 3 and 4, we divide the scroll factor by half each time. We use the scroll factor to scale the player's X velocity, so a smaller value will cause a particular layer to scroll slower. If we start walking now, we see the background scrolling at different speeds, and we get a beautiful parallax effect. We're going to continue prettying up the game by adding some features that lets us draw some background and foreground textures that are not going to interfere with our collision detection, but are there just for aesthetic purposes. If you recall, we added a brick and a grass texture earlier along with the other tiles that we loaded. We're going to draw the grass texture in the foreground and the brick texture in the background. So let's go back to our GameState and add two more vectors of GameObjects, background tiles and foreground tiles. I'm keeping these tiles in separate arrays even though we already have a layered drawing setup. When we start optimizing the game later, we can adjust this and keep everything together. Now let's go to our createTiles function and make a copy of the map array. Then just copy the first row so that you have 5 rows of zeros, creating a blank map. Then we're going to add a bunch of 5s that are essentially going to be on top of the 1s that are laid out in the first map array. These are going to be our foreground grass tiles. Now we're going to make a copy of our foreground array and call this background. Here we're going to add our background brick texture, which is usually surrounded by other tiles. So what I'm doing is looking for spaces that are surrounded by other tiles in the first map and placing 6s there, so all of the brick textures are enclosed by either ground or panel tiles. And since we now have multiple map layers, what I'm going to do is take all of the map loading code and I'm going to put it inside of this load map lambda, capturing our state, game state, and resources by reference. Then I'm passing a single parameter which is called layer, which is a pointer to our 2-dimensional array. And inside the body of the lambda, I'm renaming map to layer. This way we can pass different maps as layers to our lambda, and at the bottom of our createTiles function, we can call this lambda 3 times for the different map layers. And now back to the switch inside of our load map lambda, we create a case 5 and 6 for grass and brick. Then we create our tiles just like we did previously. We create objects of type level. For the case 5 grass tile, we use text grass and we push it inside of the foreground vector. And for case 6, we use text brick and we push it inside of the background tiles. Now we can scroll down to the drawing code, and before we draw all of the game objects, we can draw the background tiles, and then of course all of the game objects would be drawn on top of them. All we do is loop through all of the background tiles and create an SDL Rect for our destination. This is going to be the X and Y position of the object and the width and height of the texture. Then we simply call SDL render texture with our renderer, the texture in the object. We don't use a source rect and we pass our destination rect. Then we can copy the background tile loop and paste it underneath our GameObject drawing code and change the vector from the background tiles to the foreground tiles. So we draw the background, then the GameObject, and then the foreground. But if you remember what we did in the previous section, we have to subtract the map viewport X position from every object when we draw. Otherwise, we end up with what you see on screen. The tiles are just floating with the player. So inside of both of our new loops, we just subtract map viewport.x from the X position in the destination rect. Now when we run, everything's where it needs to be, and it looks great. One thing I want to note is that we might want to turn on VSync by going into our initialization function and calling SDL set render VSync right after we initialize our renderer. Calling this function with an argument of 1 will make it run for every single refresh of our screen. The game is currently running as quickly as it can, so turning on VSync will get that under control and not burn through our CPU as much. We can revisit this further later on when we start to optimize everything. Now that we have most of our drawing code set up, let's start adding some more gameplay elements. First thing I want to do is add the ability to shoot. So we're heading over to GameObject.h, and we're going to be adding a new object type called bullet. After that, we're going to add a structure called bullet data. Bullet data is going to hold the bullet's current state. So in order to support that, we're going to add another enum called bullet state. It's going to have moving, colliding, and inactive. Now we can add our state field to our bullet data struct, and make sure to initialize state to moving in the constructor. All that's left to do is to add bullet to our data union, and we're ready to use it. We're also adding another vector of game objects called bullets, because I want to keep the bullets separate from everything else. Eventually I can merge everything into the same objects array, but for now this will be easier to work with and demonstrate. Now we can add a couple more tilesheets. One is our animated bullet that flies through the air, and the other is for when the bullet collides with a surface. Nothing new to comment on here. We load these just like we've loaded everything else up until now. And now we follow the same thing we did for the player animations. We add a couple of indices for the bullet moving animation, as well as one for when it collides with something. Then we just add another vector called bullet anims, and this will hold both of the animations. We resize that vector to 2 since we have 2 animations, and we define a couple of animations to go into it. Now let's head over to our update function inside of our player idle case and add a check if the J key is pressed. We're going to use that as our fire key. Check if state.keys SDL scan code J results in a true. And if that's the case, we're going to create a bullet object. We set the object type to bullet. We set the object's direction to the same as our player's direction. We set the texture to the bullet, which is our flying sprite sheet. We set the current animation to the moving animation. And we give it a collider. The collider is going to have an x of 0, y 0, and a width and height that's based on the height of the sprite sheet image. Each frame is a 4x4 square, and we're going to get that value from the height of the tile sheet instead of simply hard coding it. And of course we need to give the bullet some instant velocity so that it fires out of the gun instantaneously. We take the player's current velocity and add a value of 600, making that the bullet's x velocity. This is to ensure that the bullet always travels at the same speed relative to the player. Finally, we give the bullet object its animations and set its position to the current player's position, for now. Then we just push the bullet into the bullet's vector and we're ready to move on. Now to draw the bullets, we create another for each loop just before we draw the foreground tiles and iterate over the bullet's vector. We do have to make a small change to our drawObjects function and add a width and height to the parameter list. This is because we previously had the sprite size set to 32 and our bullets are 4x4 pixels. After adding the parameters, we can update the code for the source and destination rects and make sure to use those values. We can also remove the sprite size constant, and of course we need to update the function declaration at the top of the file. Be sure to update the loop that draws our game objects and pass the tile size constant for the width and height. Our code won't compile if we don't do this. Now back in our bullet draw loop, we can call drawObjects and pass the bullet collider's width and height as our new parameter values. Let's also create another loop to iterate over our bullets and update their physics and animations. We'll just copy the game loop that updates the game objects, place it right below it, and change to the bullets vector. Now we're calling our update function on each bullet and updating its animations. When we run the game now, we see a few different problems. For starters, no matter what direction I'm facing, bullets are always traveling to the right. We'll quickly fix this by multiplying our bullet velocity vector by the player's direction. This will change the sign of the bullet's velocity vector depending on which way we're facing. Since a direction of -1 is to the left, a negative velocity will make our bullets travel to the left. Next, the bullets are firing out really tightly packed, which looks terrible. What we'll do is utilize a timer here, which will let us control the fire rate of our weapon. Let's head over to our player data structure and add a timer object called weapon timer. We'll initialize this timer object to a length of 100 milliseconds and head back to our bullet code. Just above the start of the switch block, I declare a reference to the player's weapon timer. I do this so I can avoid having to write out the path to the object each time I refer to it. Then we need to make sure we call its step function so that it can progress each time the player's update is run. Now we can wrap the entire block that creates the bullets in an if that checks if our weapon timer has timed out, and then immediately reset the timer if that's the case. We need to make a quick change though to our reset function to ensure that it resets the timeout flag to false. We need to add this, otherwise isTimeout will always return true after the first timeout and won't actually control our fire rate. Once we make this change, let's run the game and see a much nicer rate of fire. The bullet's initial position still looks pretty bad though. We can tackle this next. We're going to create a GLM vec2 and set a much nicer looking starting position for each bullet. Let's use the player's X position again, but for the Y position, we'll set the half value of our tile size constant, placing the bullet roughly halfway down the player sprite. That's better, but the X position is still clearly pretty bad. The bullets are always spawning from the leftmost edge of the player sprite, which is obviously wrong. What we want is to spawn bullets on the left side if we're facing to the left, and from the right when we're facing to the right. I also don't want the absolute left and right edges of the sprite in order to account for the player's gun position and the bullet's width. What I'll do is choose better margins here and use linear interpolation, or LERP for short, to change the bullet's starting X position and simply interpolate between them depending on the player's direction value. This avoids any branching if statements checking the player's direction and uses a simple calculation instead. We first define two variables for the two possible X positions. The left value is 4 pixels to the right of the left edge, and the right value is 8 pixels to the left of the right edge in order to also account for the bullet's width. Next, we calculate the value of t, which will range from 0 to 1 and be used to interpolate between the left and right values. Recalling that the value inside of our direction can be either -1 or 1, we need to change it so that it can range from 0 to 1. To do this, all we need to do is add a value of 1 to our direction, which results in values 0 or 2. Next, we just divide that result by 2, which will result in a value of 0 or 1. Then it's just a matter of writing the standard LERP equation, which multiplies our right value by t and adds the result to the value of left. This gives us our X offset, which we can add to the player's X position and get the final value of our bullet's X coordinate. I'm going to nudge the bullets down one more pixel. Now I can fire much nicer looking bullets, but only while I'm standing still. If I'm in the jumping state or the running state, the fire key isn't doing anything at all. This is because we only check if the J key is held inside of the idle state. Let's refactor things a little and ensure our running and jumping states can also be used to shoot. Before we move on to that though, I'd like to add a couple more values to our state information message at the top left of the game. I'm going to include an indicator for the number of objects inside of our bullets vector, as well as the current value of our player's grounded state. Cool. That information will come in handy shortly, but for now, let's continue with the shooting mechanics. We'll take all of the code we've written to check the fire key and spawn bullets, and wrap it inside of a lambda called handle shooting. I love using lambdas this way to reuse code, and since they're compile time constructs, the compiler will just optimize them away and not call any functions at all. Yet they let us not have to repeat ourselves, they capture variables around them, and don't require us to define entirely separate functions that we have to maintain. The handle shooting lambda will capture the state, GameState, resources, GameObject, and weapon timer by reference, so we can use them directly in the body of the function. Let's add a call to handle shooting right above the code that sets the idle texture in animation, and move the lambda right outside the switch underneath the timer step call. Now it's just a matter of going to the running and jumping states and calling handle shooting right above each state's texture and animation code. And with that simple change, we're able to stand, jump, run, and spray bullets all at the same time. That's great and all, but what would make this look better is if we utilize the sprite sheets I've made for the player shooting animations. To accomplish this, we'll add a few parameters to our Lambda, a pair of SDL texture pointers, and a pair of animation indices. Each player's state has a different shooting animation, so these parameters will let us pass those with each call to handle shooting. Inside the Lambda, we'll first set the provided shooting texture and animation within the shooting block of the code. Then we'll add an else block and set the texture and animation for the non-shooting variant. We need to load 3 more sprite sheets to our resources. We have sprite sheets for standing and shooting, running and shooting, and sliding and shooting. We'll add 2 more animations as well, one for standing and shooting and one for sliding and shooting. The running and shooting animation will simply be a sprite sheet texture swap, and we'll use the same animation object as the regular running animation. This makes it easy to seamlessly switch between running and shooting without any animation glitching. We have to switch between the running and shooting animations on the exact same frame number, otherwise there's a jarring glitch in the run cycle. If we had 2 different animation objects, we would have to keep them in sync at all times to ensure we can switch seamlessly between them as the player holds down the shoot button and lets go while running. What we'll do is use a single animation and simply switch out the sprite sheet textures, both of which have the same number of frames. This way we don't have to worry about multiple animations and having to keep them in sync. Going back to our handle shooting call sites, we need to provide the appropriate texture and animation pairs. The idle state gets the idle texture and animation for standing still, and the standing and shooting animation when firing. The running state will be a little more complicated. If we enter the sliding block, we want to use the sliding texture and animation, or the sliding and shooting texture and animation, depending on our firing state. Otherwise, we'll use the running texture for regular running, and the running and shooting texture when firing while running. Both will use the same animation index, like I said earlier, to avoid having to synchronize 2 different animations for the running cycles. The jumping state gets the exact same treatment as the running state since we're reusing the running animation when jumping. And with that, we can now see the muzzle flash and shading on our character as he blasts away his weapon. Let's look at making those bullets interact with the environment though. We don't want them just flying through the level like this. Before we add collision detection for the bullets, let's quickly look at how we can add some helpful visualization for the colliders. Collision detection is hard to debug. It's useful to know how we can visualize the hitboxes involved. Let's add a Boolean variable in our GameState struct that will let us toggle debug mode on and off. Initialize the variable to false in the constructor and head over to the event handling loop. In the keyUp event, after the call to handle key input, we'll check if the key being pressed is F12. If that's the case, we can toggle the Boolean value inside of the debug mode variable. We can now move our existing debug information message to only display if debug mode is enabled. All we have to do is wrap the code that renders our message inside of an if block that checks if debug mode is true. And now hitting the F12 key will toggle the display of this message. Let's also revisit the drawObject function and add another if block for our debug mode variable. It's here that we're going to draw our collision hitboxes when debug mode is enabled. What we'll do is copy the code for Rect A in our check collisions function, and then copy it inside of our new debug mode block. Change the variable from A to OBJ, which is the current GameObject that we're drawing. Now we need to set the draw color for the collision hitboxes by calling SDL set render draw color and selecting the color red, or whatever color you'd like. Just remember to put 255 in the last parameter for the alpha value. And now we can call SDL render fill rect to draw the filled rectangle, visualizing the collision box of any object that we draw in our game. Once again though, we need to offset the x value in the rect by subtracting map_viewport.x in order to draw the collision boxes correctly. And there you have it. We can now see every collision box in our game. Later on, this type of debugging will be invaluable once we start adding things like game event triggers or other objects with custom collision boxes. What would make this even nicer though is reducing the alpha value on these collision boxes and being able to see the game sprites through them. Let's set the alpha value in the set render draw color to 150, adding some transparency to our collision boxes. Then we'll call SDL set render draw blend mode, passing SDL blend mode blend before calling our draw command. After drawing, we set the blend mode to SDL blend mode none to disable blending again. We're not drawing our regular sprites with alpha blending enabled as of now, but that may change in the future. Now when we enable debug mode, the collision boxes are a little easier on the eyes. Speaking of debugging, I'd like to show you a bug in the game that you might not have noticed if you're following along in coding. In some cases, when we're jumping to the ground, we can get stuck as shown on the screen. No matter how hard I run, the game isn't letting me get past this entrance. The reason this is happening is that after falling to the ground, the gravity is still trying to push our player down further, even though we're on the ground. So what's happening is our character is being pushed slightly into the ground tile, causing the collision detection to stop our movement, and then we get pushed back out of the tile. Of course, the game is drawing our final position, so you can't see this occurring, but it does indeed occur every frame. The reason why it's happening is that we should be applying gravity to our player only if we're not currently in a grounded state. All we need to do is head over to the gravity code and add another condition to the if block, making sure we're only applying it if the current object is not grounded. And with that change, the issue will no longer occur. But now another bug has popped up. When we jump against the walls, the game seems to think that we're grounded and stops applying gravity like we told it to. We aren't grounded though, we've simply collided against the wall horizontally. Why would this be happening? It's because we're using SDL has Rect intersection float rather than SDL get Rect intersection float. And it appears that the has Rect intersection variant is returning true when it shouldn't. As far as I can tell, this shouldn't be the case, and I've spoken with people on the SDL Discord and they agreed that there shouldn't be a difference here. But yet there is. So my advice is to simply not use has Rect intersection and always use get Rect intersection, regardless if you actually need the result in Rect C for the collision resolution. And while I'm working on this bit of code, I'm going to add another if block that only does the grounded checking against level tiles, since landing on other tiles like enemies shouldn't change the player's grounded state. And with that, things are now working great and we can hop around without issue. Also note that I've added another draw command showing the sensor rects that we're using to check if a tile is grounded. That's the little blue bar underneath the tiles. Okay, cool. Now let's finally get back to making our bullets actually useful. First, let's head over to our update function and move a couple of things around so that all our object types can take advantage of our movement code, not just the player type as it currently is. Let's start by moving the code which applies acceleration to our velocity out of the player block and place it directly above the line which updates the object's position. Now any object type in the game will be affected by this. But now the block of code can't see the current direction variable. Easy enough to fix, we'll declare that variable outside of the player block just below the gravity code so all object types can see it. I'll also move the code that changes the object's direction variable underneath the chain of ifs that will perform the object type specific updates. This way we have access to the object's previous direction by checking the object's direction variable, and then we can get the current frame's direction by using the, current direction variable. Okay, now our bullets seem to be frozen in space after we fire them. What happened to their velocity? Well, since all object types, including bullets, are being affected by the acceleration code that we moved, this bit of code checks if the velocity has surpassed our maximum speed, and if it has, we clamp it to the maximum speed value. Except our bullets currently have a maximum speed of 0. So this code stops them in their tracks. All we need to do though is give the bullets a high maximum speed value and we're good. Okay, now our code is more generic and our bullets are flying again. But take a look at our debug section. If you recall, we just create the bullet objects and push them into our bullets vector. This causes the bullet object count to keep growing indefinitely. This will eventually be a problem if we start having to check collisions on hundreds or thousands of bullet objects every frame. Let's see how we can eliminate this issue before we start checking for collisions. Recall that one of the bullet states we added is inactive. We'll use this state when a bullet has left the viewport area or has finished colliding with an object. Then when we fire a new bullet, we'll simply reuse an existing inactive bullet, breathing new life into it, or just pushing a new bullet object if we can't find one that's inactive. Let's see what that means. We'll start by heading to our bullet spawning code inside of the handle shooting lambda. Just before we push a new bullet, let's begin by declaring a Boolean variable called foundInactive and initializing it to false. Then we add a for loop that iterates through all the bullets in our vector and runs while we haven't reached the end of the loop and while foundInactive is still false. We don't want to keep looping if we've already found an inactive bullet. Inside the loop, we check if a bullet is inactive, and if it is, we set foundInactive to true and assign the current bullet details into our current vector element. This causes the loop to end, after which we can check if foundInactive is still false, and if that's the case, we can still push a new bullet into the vector. This will now reuse inactive bullets inside the vector rather than constantly pushing new ones. This will now reuse inactive bullets inside the vector rather than constantly pushing new ones. Okay, if that's so, then why is our bullet counter still growing in game? Well, as of now, there's nothing actually setting any bullets to inactive. So let's head over to the update function and add an else if block for objects of type bullet. In here, we'll check if the bullet's position is outside of the map viewport area so that we can flag it as inactive once it's out of view. Let's check if the bullet's x position, offset by the viewport's x position, results in a value less than 0. If true, that means that the bullet is past the left edge of the screen and we can set its status to inactive. If we run the game and start shooting to the left, we can see that the bullet vector never goes higher than 6, which is the maximum number of bullets we can see at any given time at their current velocity. Turning to the right though, the bullet counter starts growing again. Let's add a similar check for the right side of the screen. Add a Boolean OR and check if the x position is greater than the logical resolution's width, which is what we're using for the viewport width. Now our bullets will be flagged as inactive regardless of whether they're going off the left edge or the right edge of the screen. And while we're here, let's add 2 more checks for the vertical axis, checking the bullet's y position and using the logical resolution's height. Same principle, different axis. The time has finally come to add collision detection for our bullets. And since we have all of our basic gameplay elements in place now, adding it will be a breeze. Just hop on over to our collision response function and add an else if block for bullet object types. It's here we can respond to bullet collisions however we'd like. Then we'll create a switch block for the various bullet states. Add one for the moving state and zero out the bullet's velocity when a moving bullet makes a collision with an object. Seems like the bullet velocity isn't being affected though. And actually, the bullet state variable has a value of 204, which is just some junk data. Since I've forgotten to create and initialize the bullet data struct when spawning bullets, this is the result of my sloppiness. Nothing to worry about, it's just a matter of creating the bullet data struct and assigning it to the bullet data field. Now all new bullets will have their data field initialized properly and have an initial state of moving. When our bullets collide with the level tiles now, they stop in their tracks. But this isn't really that nice. Let's take the collision code we wrote for the player type and once again use a trusty lambda so we can reuse it for all kinds of different objects. We'll put the code inside of a lambda called generic response, and we can now use it whenever we need an object to have a basic collision response against other objects. We can now call generic response from the player level collision case as well as the moving bullet case. Now when a bullet collides with a tile, the generic response lambda moves it out of collision and cancels its velocity on that particular axis. Since our bullets have collided with an object, let's change the state accordingly, and also update their sprite sheet texture and animation to match. Okay, so the collision animations now play, but we can't have them looping endlessly like this. Let's add a getter to the animation class called isDone, which we can use to tell if an animation has completed. We can simply return the result of timer.isTimeout and forward the result. Then we'll head over to our update function again and add a switch for the bullet state. We can perform different updates to our bullets depending on their state this way. Let's move the code that sets the out of view bullets as inactive into the moving case. This way only moving bullets will be checked by it. Then we'll need a case handling bullets that are in the colliding state. In this block, we can check if the colliding animation has finished playing, and if so, just change the bullet state to inactive. Let's also make sure that we don't call drawObject for inactive bullets, since we shouldn't be seeing them on screen. I think this is looking pretty good now, but with a minor tweak, it will look a little better. At the moment, the bullets are flying out in an absolutely straight line, but I think adding a little bit of recoil and variation will make things better. We'll go over to the bullet spawning code and add a variable called yVariation, initializing it to 60. I'm just using an arbitrary value which will change the y coordinate of our velocity vector. I'll use the SDL rand function to generate a random value between 0 and 60, and then subtract 30 from the result. This will give us a random value of -30 to 30. Now I can just plug the result into the velocity's y coordinate, and our bullets will spray out with a small arc rather than an artificial looking straight line. Maybe a random value of -20 to 20 might be better, so I'll change yVariation to 40. A little more subtle, but you can set it to whatever you like. Also notice here that as I'm jumping, every once in a while a bullet will collide and then fly through the level tiles. This is because the generic collision response will only affect the velocity on the detected axis of collision. Sometimes these bullets will collide on their vertical axis, and only their y velocity will be affected, but obviously their x velocity is what is driving the majority of their movement. Let's just scale the velocity vector by 0 after the generic response and call it done. This resolves the issue. Beautiful, now we've got a fairly robust shooting mechanic at our disposal, but it's kind of useless since we have nothing to shoot. I went ahead and created this creepy looking guy for us to attack and made a few different animations. One for idling and shambling, one for when he's taking damage, and my proud achievement, his juicy death. To get started, let's add 3 more texture pointers to our resources struct and load the images as per usual. Then we'll add another vector to hold the 3 animation objects, as well as more animation indices. With those in place, we can define the animations themselves. We've got the default shambling animation, which is 8 frames and 1 second long. The getting hit animation, which is also 8 frames and 1 second long. And the death animation, which is a whopping 18 frames and 2 seconds in length. Now we can revisit our tile maps and add a number 3 tile, which represents enemies, somewhere for us to test with. We also need to add a case 3 in our switch block so we can create the enemy. And inside there, we'll create the enemy object, set the default animation. We need to make sure to copy the animations in there, and then we can push the enemy object into our characters layer. Watch how big this guy's hitbox is though. Let's bring that down so it looks nicer. These collider values work pretty well. Take a look at how it looks now. This guy still doesn't look like he's being hit though, so let's change that. We'll add a new enum called enemy state so we can control his behavior. We'll add a shambling state for when he's idling and wandering, a damaged state for when he's being shot, and a dead state for when his health runs out. Add a single state field to the enemy data struct and set the default state to shambling. And if you're following along, you might already have an enemy data field in your object data union. If not, add it so you can get enemy-specific data fields. Let's go back to the bullet collision handler. Inside the moving case, we'll add another switch to define how different objects react when hit by a moving bullet. We'll add a case for level object types, but leave it empty for now. And then add another one for when an enemy object is hit. As an initial test, let's make it so that enemies turn and face us when hit by a bullet. All we need to do is set the enemy object's direction field to a negated version of the bullet's direction value. It would also be pretty nice if we make him flash while he's taking damage. Let's see how we can do that. Head on over to the GameObject struct and add a timer object called flashTimer, and initialize its duration to 50 milliseconds in the GameObject constructor. This timer will dictate the duration that an object should be highlighted during a flash interval. A simple approach might be to alternate the flash interval every other frame, but using a timer makes it much more reliable and frame rate independent. Now add a boolean field called shouldFlash and initialize its value to false. We'll use this to signal a flash interval. Back in the bullet to enemy collision handler, let's set the enemy's shouldFlash field to true and reset the flash timer. This will ensure that the target object always highlights when it's hit. Now go over to the drawObject function. If an object doesn't need to flash, we'll just draw it as usual. If the shouldFlash field is set to true though, we'll call the SDLSetTextureColorModFloat function to provide scalar values for each color component of the texture. Then when the renderer draws that texture, it will scale each color component by the provided float values. In our case, we'll set a value of 2.5 for the red component, which will increase the red intensity by 2.5 times. The rest of the color components remain unchanged. After setting the color mod values, we'll render the sprite the same way we normally would, and then immediately reset all the color mod values back to 1. We need to make a change to our timer class. Head on over to it and set the step function's return type to bool. We'll return a value of true if the timer has completed, and false otherwise. Now just below the highlight drawing code, we'll call the step function. This is so the object's flash timer will only run while the object is in a flashing state. Once the step function returns true, signaling the timeout, we set the shouldFlash flag to false, causing the highlight interval to end. Shooting our new enemy now results in a satisfying flashing animation. Let's also make him animate differently when being hit. All we have to do is set the sprite sheet and animation in the collision response, and the enemy will now look like he's being struck. We'll also need to make sure to change the enemy's state to damaged so we can perform a different update when the enemy takes damage. Once again, let's make sure that the GameObject has its appropriate data initialized. We'll create an enemy data object and store it in the enemy's data field. So now the enemy flashes and changes animation when being shot. But as you can see, he forgets to go back to shambling after taking damage. We'll add another timer object in the enemy data struct and set its duration to half a second. Now in the update function, we can add a block to handle enemy game objects and also set up a switch for the enemy's state and handle the damaged case. In here, we'll step the damage timer, and on timeout, change the sprite sheet, animation, and state back to shambling. Now when an enemy gets damaged, it'll stay in that state for half a second, then go back to shambling. We still can't take this guy out though, so let's head back to the enemy data struct and add a field called health points and initializing it to 100. In the collision response handler, when a bullet hits an enemy, we can subtract 10 points from the enemy's health points. I'm also setting up a reference to the data object so I don't have to constantly drill into the enemy data field, which will make our code a little more concise. Next, check if the health has dropped to or below 0, and if so, we can change the enemy's state to dead and play the appropriate animation. We now get the death animation, but there are two small issues. We can still hit the enemy even though they've expired, and the death animation just keeps looping forever. Let's first set up our code so we can tell bullets to ignore collisions in certain situations, such as intersecting a dead enemy. At the top of the bullet collision response block, add a bool called passthrough, initializing it to false. This variable will dictate whether bullets will respond to a collision or simply pass through. In the bullet into enemy collision block, we'll make sure that all of the code only occurs for non-dead enemies, and add an else block if the status is dead. In here, we'll set passthrough to true. Then at the bottom of the bullet collision handler, wrap the generic code in an if, ensuring it only executes if passthrough is false. Now we have an easy ability to ignore object collisions in the bullet handler and make the bullet particles ignore dead enemies. Okay, all that's left is to stop the death animation from endlessly looping. At the moment, all objects we draw will get their current frame from the current animation object, or simply use sprite frame 1 if no current animation index is assigned. What I'll do is add a new GameObject field called sprite frame. Initialize it to 1, and then inside of drawObject, we'll use this to calculate the X position within the tile sheet. More on this in a second. I'll need to make a small change to ensure the order of operations is correct in our game loop. At the moment, the animation gets processed after the update function has run for a given object. This looks fine visually, but it means that the update function doesn't know if an animation has finished until the next frame, since the animation updates happen after the object updates. What I'll do is move the code to progress the animations inside of the update function and place it at the top. This way we accomplish two things. One, the animation update code happens in a single place, and that's better for maintenance. And two, animations progress prior to object updates, allowing the update code to respond to animation changes on time. We'll check if the death animation has completed by calling its isDone method, but we should only do this after checking if there's actually a current animation, since after the next update, dead enemies will not have an animation after it plays once. If the death animation has completed, we'll set the current animation index to -1, forcing the drawObject code to use the current frame field instead of the animation. And we'll also set the current frame to 18. This is the last frame in the enemy's death animation, which is just a pile of gibs on the ground. In case you didn't catch our drawing bug, our code will currently draw the sprites starting at X position 18 in the tile sheet, not frame 18. Currently, we're just subtracting a 1 from the sprite frame number in order to turn it into an index, but this code expects an X position, not a frame number. So we take a hint from the line above. All we gotta do is multiply it by the sprite width in order to get the correct X position within the sprite sheet. Now this is what we're looking for. Let's add a few more enemies and see how they show up in the game. I'd also like gravity to affect enemy objects, so we can just set them to dynamic in the enemy spawning handler code. And now, the falling enemy just goes right through the floor since it doesn't have any collision response handling. It's just a matter of adding an enemy block in the collision response function and calling generic response inside it. Now our enemies will interact with the environment better. And now, through the magic of television, we'll create a more comprehensive level to jump around and shoot in. One of the more difficult topics in game development is artificial intelligence. Because of this, I'll create dedicated videos to that topic in the future. With that said, let's take a few minutes and see how we can make our enemy's shambling state actually shamble towards us. Let's head over to the update function and add a case for the enemy shambling state. Now we'll create a vector that will point from the enemy towards the player. We do this by subtracting the enemy's position from the player's position. Once we have this vector, we can use the glmLength function to get the distance between the two objects. If the distance is less than 100, let's get the enemies to start moving. We first update the current direction variable. If the enemy to player direction vector has a negative x value, we'll set the current direction to -1. Otherwise, we'll set it to 1. This will ensure that enemies will have the correct direction if they are close enough to the player. Now we just need to give the enemy some acceleration. A value of 30 in the x coordinate will do. If the enemies get far enough from us, we can stop them from moving. We do this by removing their acceleration and setting their x velocity to 0 in the else block. We should also set their x velocity to 0 in the dead case handler, since we don't want them moving while dead. Our enemies still won't move though until we give them a maximum speed. Head to the createTiles function and in the enemy case, set the max speed x value of the object to 15. For an added bonus, let's make our player bounce off enemies when he collides with them. We'll head to the player collision response handler and add a case for the player and enemy collisions. In here, we'll simply set the player's velocity to the following vector and multiply it by the negated value of the player's direction. Of course, let's wrap this up in an if block, making sure we're not bouncing off of dead enemies as well. This will cause the player to bounce off when making contact with enemies. If you'd like, feel free to improve this and add health points to the player type. You can make the player take damage during this collision. I'll leave that up to you, since at this point you have all the know-how to code this easily. Feel free to play around. We've definitely come a long way. We have a very solid foundation that we can build on top of and add more sophisticated and interesting gameplay features. I'd like to pause on the gameplay front though and touch on audio. SDL3 has introduced a fantastic new audio system that can be used to play, mix, resample, and manipulate audio. Even though it offers everything we need, it might be too much for a beginner to just dive right into. So we'll give the SDL3 audio system the respect that it deserves and discuss it in a separate video. If you're curious about it now, I recommend checking out Ryan C. Gordon's video on the new audio system. I'll leave a link in the description. Most games can go quite far without sophisticated audio features, and simply require the ability to play and mix music and sound effects, without worrying about all the complicated audio pipework underneath. Enter SDL Mixer, another of the standard SDL adjacent libraries, designed to be easily integrated and used, doing almost all of the heavy lifting when loading audio formats, streaming and looping music, and multi-channel audio playback. The only thing is, we're using SDL3, and at the time of recording, there's no official release yet. That said though, SDL Mixer works very well with SDL3 already, and will likely have an official release very soon. Now, if we weren't seasoned CMake users by now, this might have been an issue for us, and we might have even considered passing up the library in favor of the new SDL3 lower level library. But we won't. So what we'll do is build a library ourselves from source and install it as a package that we can link with our game. This is super easy to do, so let's get to it. I'd like to remind everyone that despite the fact that I'm doing this on Windows and using the Visual Studio toolchain, the process is identical on other platforms, give or take some path differences. First thing we'll do is clone the SDL Mixer source code and make sure to include the recursive directive so that the required third-party submodules are cloned as well. Next, we'll run CMake -s SDL Mixer -b build SDL Mixer to set up the build directory from the source we just cloned. And if you're on Windows or have a specific path to the CMake library you're using, also provide -d and the CMake prefix path variable specifying that library path. This will create a build for our compiler toolchain. Now you can run CMake -build and the path to the build directory, and if you're on Visual Studio, -config and then release to compile a release build. If you're a non-Visual Studio user, you can run the previous command and provide the CMake build type variable to select either debug or release build types. Once the library is built, we can install it somewhere by running CMake -install and the path to our build directory, and once again, if on Windows, specify the build configuration using the -config release directive. And don't forget, the CMake install command can also take the prefix directive to specify the path where we want to install the library. And that's all there's to it. We can now tell our game project where to find the library and start using it. Head over to the CMake user presets file and add another path specifying the new library installation. Now head over to the CMake list.txt file and add another find package call specifying SDL3 Mixer as required. And then also add SDL3 Mixer :SDL3 Mixer to the list of target link libraries. Once you save or reconfigure the build with CMake, you can start including the SDL3 Mixer headers and get to coding. We'll start by loading a few chunk objects with SDL Mixer. Chunks are what SDL Mixer calls the audio buffers we've loaded in memory. We'll follow the same setup we made for the SDL texture objects. Add a vector to hold mix chunk pointers, and then create a load chunk function. Here we'll load the chunk from file by calling mix load wave, set the default volume for the loaded chunk by calling mix volume chunk, passing the pointer and the volume level. We're setting all new loaded chunks to half the maximum volume level. Then we push it into the new vector and we return it. We should also quickly go to the unload function and add a section that loops over all the loaded chunks and calls the mix free chunk function on them, releasing them when the game unloads. Then let's create a couple of mix chunk pointers that we'll need in our game. Chunk shoot, which is our shooting sound, and chunk shoot hit, which will play when a bullet collides with a level tile. Then we can just load the two wave files by calling load chunk inside of our load function like we're used to. If we run the game now, we'll get a familiar error letting us know that the SDL Mixer Runtime DLL isn't anywhere to be found. We'll let our game know where to find it by adding the bin directory of our SDL Mixer installation to the path variable, just like with the other libraries. Remember, you can also just add these paths to your system path or copy the DLLs in the same directory as your executable. I just prefer this approach because it doesn't affect my system and doesn't involve copying any files every time I rebuild or clean the project. Before we can play any audio, we'll need to initialize the audio system. Head on down to the initialize function and at the bottom, add a call to mix open audio, requesting the default audio device by passing the SDL audio device default playback constant for the first parameter. And we'll let SDL figure out the audio output specs that'll work well for us. If you want to configure the audio format yourself, this is where you'd pass a pointer to an SDL audio spec instance and configure everything you need. Now let's tell the game to make some noise. In the bullet spawning code, make a call to mix play channel. Passing -1 to the first parameter tells SDL Mixer to use an available audio channel in order to mix the audio with anything else that might be currently playing. Then we tell it the chunk we would like to play and pass 0 for the last parameter, telling it that we don't want to loop at all. Now let's go to the bullet collision response handler and add a case handling the bullet and level collisions. Then we can just play our sound effect by making another call to mix play channel. While we're at it, let's load another audio chunk to play when we hit an enemy. And then go over to the bullet enemy collision handler and play it from there. And to make things a whole lot better, I've downloaded a song from OpenGameArt that'll play when the game starts. Details in the description. To load the song, I'll create a pointer to a mix music object in the resources struct. Then make a call to mix load muse in the load function, providing the path to the MP3 file. I also won't forget to free the music object in the unload function. And now to play the music, let's just call mix play music right before the start of the game loop, passing the pointer to the music object and a -1 for the second parameter, telling SDL Mixer to loop the song indefinitely. Since I know the music is quite loud, I'll make a call to mix volume music and set the volume for this music object to 1/3 of the maximum volume. Let's also quickly add a Fullscreen Toggle feature so that we can see the game in full glory. Add a bool variable inside of the SDLState struct called Fullscreen and initialize it to false. Then head over to the event loop and add an else if in the key up event, checking if the F11 key is pressed. Inside this handler, we'll first toggle the boolean variable and follow that with a call to SDL set window full screen, first passing our window pointer and then the full screen boolean. With this in place, the F11 key will toggle full screen mode for us in-game at any time. Now let's run the game and enjoy. Thank you for watching the video. I hope you learned a lot while you were with me. This should give you a strong foundation in beginning game development, but there are many more topics that we're going to need to cover in future videos, such as enemy AI, optimization techniques, collision optimizations, and so on. I'll be diving into all of these topics in upcoming videos, so be sure to subscribe, like, and share this video if you enjoyed this content. Once again, thanks for watching and see you soon.